Hey, Nate here, popping in really quickly before the start of this pretty long video, just to explain what this is. So I've started conducting free classes over MCAT content over on my website. They're entirely free and come with an accompanying set of notes and an Anki deck just to make your life a little bit easier. So I highly recommend checking them out and signing up if you're wanting to have like a live class that goes over this sort of content. And again, it's entirely free, so definitely recommend checking out the link in the description of this video. This is a recording from my first lecture that we talked about acids and bases. We'll, of course, be covering a few more topics throughout the fall, including fluids, metabolism, cell cycle, repro stuff, that sort of type stuff. And of course, I'll be announcing some other topics as we get into early next year. So again, just recommend checking that stuff out. Two other things that I want to mention really quickly. The first is that part of this lecture where I talked about some acid-base solubility for some reason didn't record properly. So in addition to everything that I covered here, you're going to want to make sure that you know that acids are more soluble and will dissociate more in basic solutions and vice versa for bases in acidic solutions. That's all in the notes that are in the comments of this video, or description of this video that I should say, just in case you're also wanting to follow along and get everything that you need to know. I also messed up on some math problems whenever I was making these slides, so that's my bad on that. I fixed it in the session, and obviously, of course, I fixed it on my slides, so they'll be perfectly fixed for any future lectures I do on acids and bases. But that's it. If you enjoy this lecture or the style of it, please feel free to sign up for any of my others coming later this fall, of course, at the link in the description. But in order to get the most out of this lecture, like I said, have those notes up so you can kind of refer both to both pages. There are like a few graphics and things that I'm missing from the notes that I will add. Yeah, that will make sense as soon as we kind of get to a few of them. And like I said, you can open the link, hit file, and hit make a copy, and it will allow you to edit anything that you want. You can add any notes, make any clarifications that you want. That there is an Anki deck that's going to go out sometime with that recording. That's another email that you'll get. That's just mainly to help you remember the information that we talk about today. And then, of course, just practice and integrate that information as much as you can. You need both Anki memorization and practice is like they work hand in hand with each other. It's not like one or the other is going to be the best thing for the MCAT, but especially soon after this lecture, I recommend trying to integrate this information as soon as possible rather than watching this lecture and then not touching anything until a month or two down the road, just because from your initial exposure, soon after that is when you want to start integrating that information, because if you wait too long, you're going to have to learn this information again and again. So yeah, and then of course, because I have an LLC, I do want to put the disclaimer up that I can't guarantee what will or won't show up on your exam. I'm not responsible for what you score on your exam. Of course, I know that sounds obvious, but I just have to put it up just to make sure. But that doesn't mean I'm not going to try my absolute best. I can't guarantee anything, but I've been around this exam for a long time. I've been teaching it for a long time. I have a pretty good idea of what's going to show up based on the AMC materials, all that sort of stuff. And we're going to go ahead and get started. We're going to go ahead and jump into acids and bases. So like I said, there's a few things that I'm going to kind of assume that you already know, or at least are somewhat familiar coming into this lecture. So that you know, for example, like what an element is or what molecules are, just the really basic Gen Chem stuff. And you know the difference between metal and non-metal, stuff like that. You know what the different states of matter are. Technically, there's 3 states of matter. In chemistry, we use another one called the aqueous state. I'm assuming that you know what those are. I'm also assuming that you kind of know what an equilibrium constant is. We will kind of cover this a little bit, especially to make sure it makes sense with acids and bases. But that is the kind of stuff that I'm just kind of assuming that you have at least somewhat of a basic understanding of. Again, we'll kind of hit the basics as we go through, but that's the stuff that I don't have time to tell you exactly what an element is or exactly what the difference between metals and nonmetals are. So just to talk about the basic definitions of acids and bases, acids are essentially any molecule that can lower the pH of a solution. We're going to talk about exactly what pH is, but that's what an acid is. There's a lot of different ways it can do that, but acids lower the pH of a solution. Bases are going to pretty much do the opposite. They're going to raise the pH of a solution. Sometimes we call them alkaline substances because a basic solution is the same thing as saying an alkaline solution. So you might see those words used interchangeably. So there's a few different classifications of acids and bases. The first one and the most broad one is called the Lewis acids and bases. This is based on the movement of electrons. The way that I always memorized this was whenever you draw a Lewis structure, you are drawing the entire 4 hours be included in the recording. Yes, the entire 4 hours will be basically start to finish. I actually can't even really control beginning and start. I was actually in here 15 minutes early, so the entire lecture will include everything. Unless we end early, I'm not going to sit here for like an hour just for the recording. But yeah, sorry. Basically, the Lewis, sorry, I had the chat box hidden. That's why I'll try to stop at more logical times than that. But the Lewis acids are based on the movement of electrons, Lewis acids and bases. And just what I was going to say was the way that I always memorized that was through Lewis structures. Anytime we draw the Lewis structure of a molecule, we are drawing its electron structure, right? So that's how you can memorize what Lewis acids and bases. We're going to cover each of these a little bit more in the next few slides. Bronsted-Lowry is the next type of acid, which this is based on the movement of protons or hydrogen ions. It's the same thing. And then finally, the last type is the one that you're going to be most familiar with, which is the Arrhenius acids and bases. This is based on what if something's releasing or producing hydrogen in solution or hydroxide in solution. So those are the three different types of definitions. Solomon, I'll get to that in a second, where the just to kind of talk about this a little bit. Like I said earlier, the Lewis acids and bases is the most general definition. Arrhenius is the most specific. So Arrhenius acids are a type of Bronsted-Lowry acid. And Bronsted-Lowry acids are also a type of Lewis acids. So put another way, basically every single acid and base is going to be a Lewis acid and base. Not every single acid and base is going to be an Arrhenius, and we'll talk about examples. I also want to mention really quickly, this will be brought up a few times, but if you don't see a state of matter that I've specified, you can just assume it's aqueous. I'll usually try to specify, especially like the liquid and solid states of matter. All of those will be specified, but sometimes I just got a little bit lazy and didn't specify that something's aqueous. So Solomon, to answer your question, there's every single lecture topic that I have listed will eventually be free. It's gonna I'm gonna be doing one of these free lectures a month. So like this month it's acids and bases. Next month it's the cell cycle stuff. The week after that, not the week, the kind of like 4 weeks after that. Like I said, it's not going to be as sparse as once a month, but it's going to be probably a little bit more often than that, especially into early next year. I'll probably pick a different topic. I'm leaning towards waves in physics right now, so that basically there's going to be one free lecture with a different topic every single month, essentially. So there's going to be every single thing that's listed is going to be free eventually, if that makes sense. It's just going to take me time to build all of them, essentially. And then the paid lectures will be it's the exact same lecture. They're just going to be running more often than that in between the free ones. Okay. So like I said, we're going to kind of talk about each one of those types of acids and bases. We're going to start off with the most general definition, which is the Lewis ones, the ones talking about the movement of electrons. So specifically, a Lewis acid is something that accepts electrons. So for example, the molecule boron trifluoride, this is kind of what it looks like right here. This will make sense here in a second, is an example of a Lewis acid, meaning it's going to be accepting electrons from something. A Lewis base does the opposite. It is going to be donating electrons to something else. So for example, this is ammonia. Ammonia is going to be a Lewis base, where notice here it is basically passing those electrons onto boron. And in doing so, we're going to create a new bond here, just in this example. So Lewis acids, they are electron acceptors. Lewis bases, they are electron donors. And just like I mentioned on the last slide, every single acid and base is a Lewis acid and base. The next definition that we're going to talk about are the Bronsted-Lowry acids and bases. These acids and bases, like I said earlier, they talk about the movement of protons. So a Bronsted-Lowry acid, it is going to be one that's donating protons specifically. And a Bronsted-Lowry base is going to be accepting protons. Of course, these things are still considered Lewis acids and bases. So the Bronsted-Lowry acids are still going to be accepting electrons. The Bronsted-Lowry bases are still going to be donating electrons. We're just adding another layer on top of it that In addition to the movement of electrons, these things are also donating and accepting electrons. So for example, looking at this page right here, if you had to guess, do you think HCl is going to be an acid or a base? Especially since there's only a few of you actually in this lecture. Totally okay if you guys don't want to respond to anything. I'm going to offer a few chances for you guys to answer questions, but totally okay if you don't, if you want to just sit back and listen. Right, it's an acid, yeah, because it has that hydrogen that it can be donating to something else. And this Bronsted-Lowry base is going to be ammonia, because notice here, this nitrogen originally had 3 hydrogens, and now it has 4 over here, right? Bronsted-Lowry acids donate protons, bases accept them. Like I said earlier, all of these acids and bases are still considered Lewis acids and bases. Lewis, every Bronsted-Lowry acid and base is still considered a Lewis acid and base. Yes. So just to kind of show you, because I get how that's confusing, because like we're donating protons but accepting electrons for the acids. Let me finish my thought really quickly, and then we'll go through and cover like clarify the difference between the two. But the other thing that I was going to say, not all Lewis acids and bases are considered Bronsted-Lowry. So Bronsted-Lowry is a more specific definition. Every single acid is a Lewis acid. Not every acid is a Bronsted-Lowry acid. We'll clarify this on the next slide. But yeah, just to kind of talk about that. So just for example, looking at the acid definition so far. So Lewis acids are accepting electrons and donating protons, right? So let's look at this acid right here. We know that it's a Bronsted-Lowry acid, but it's also a Lewis acid as well. So looking at this chlorine molecule right here, it donated a hydrogen, right? It released a hydrogen, so of course it's going to be a Bronsted-Lowry acid. That's the Bronsted-Lowry and the Arrhenius definitions are usually the ones that are more intuitive. So it donated this hydrogen, therefore it's a Bronsted-Lowry acid. But notice it now has a negative charge, which means that in donating that hydrogen, it also received electrons, if that makes sense, to become this negatively charged chlorine. So that's basically, in order to donate those protons, it has to accept electrons. So it's doing both, if that makes sense. So the Bronsted-Lowry bases, this ammonia molecule right here, it's accepting this hydrogen to become this ammonium molecule right here. But notice that it now has a positive charge, meaning it's given up electrons to do so. So basically, even though it's weird that one's donating protons and accepting electrons, they actually have to do both of those at the same time in order to accomplish what they're trying to do. Does that make sense, Dylan? Okay, perfect. Okay, so just to kind of expand on this idea right here, that like I said, all Lewis acids, excuse me, oh my gosh, all acids and bases are Lewis, but not all are Bronsted-Lowry. We're going to bring up some examples that we just talked about. So from the Lewis acid and base slide, this is the reaction that we basically saw, right? Where I want to point out that notice in this reaction, the boron molecule is only accepting electrons from nitrogen, and therefore it's only a Lewis acid. Like, I know technically there's hydrogens that are attached to this nitrogen, but the only thing that boron is doing is accepting electrons from nitrogen. So because of that, we say that it is only a Lewis acid. Boron itself is not accepting any hydrogens. It's not bonded to any hydrogens in this molecule over here. So because of that, it's only a Lewis acid. And because it's not accepting any hydrogens, it is not a Bronsted-Lowry acid, right? Every single acid's Lewis, not every single acid is Bronsted-Lowry. Conversely, using that same example from the Bronsted-Lowry acid base slide, notice right here that this nitrogen, it has accepted a hydrogen, meaning that it, of course, is going to be a Bronsted-Lowry base, but it is also donating electrons to the chlorine, so it's also going to be a Lewis base as well. It's doing both, so we consider it both. We would more so accurately say that it is a Bronsted-Lowry base. You usually defer to the more specific type, but it is also considered a Lewis base. Both classifications are correct. Right? Any questions about the difference between Lewis and Bronsted-Lowry? Okay, I'm going to go ahead and move on. Like I said, therefore, nitrogen is both a Bronsted-Lowry and Lewis base. So the most specific definition of acids and bases is the Arrhenius definition, where anytime it's an Arrhenius acid, we're talking about what's happening in the solution because of that acid. We're not necessarily talking about what that molecule itself is doing. We're talking about what is happening in the solution because we've put that molecule into a solution, right? And like I said, these are usually the definitions that people are the most familiar with. And that will make sense as soon as we see some examples. But just like I said earlier, all of these Arrhenius acids, it's a more specific definition. So it's also doing everything that those other Lewis and Bronsted-Lowry acids were doing, accepting electrons, which is the Lewis acid definition, and donating hydrogens as well. Just in addition to those two things, these acids are specifically causing an increase of hydrogen ions in the solution. Very similar. Obviously, especially the Bronsted-Lowry and the Arrhenius definitions of acids look very similar. We're donating hydrogens to something, producing more hydrogens. But whenever we get to the base definition, you'll see why we need a more specific definition for the Arrhenius bases. So just for example, we have hydrochloric acid. It is going to be dissociating to form this hydrogen ion and chloride ion. Since it releases this hydrogen ion to water, we consider an Arrhenius acid. It is increasing the concentration of hydrogens in that solution of water. Arrhenius bases are specifically molecules that are increasing hydroxide concentration in solution. So notice with all of those other bases examples that we've talked about before, we have not even mentioned hydroxide yet, if that makes sense. So of course, they're still going to be doing the same exact things that all of the other, the Bronsted-Lowry and the Lewis bases is going to be doing all of that as well. But more specifically, these are going to be things that there's some spectator ions that are left out here, which is why it's kind of hard to see that they're accepting a hydrogen here. But basically, notice that we are releasing a hydroxide to the solution, which is going to increase the amount of hydroxide in solution. Basically, anytime you see a base that has hydroxide in it, it's going to specifically be an Arrhenius base, which means it's also the other types of bases as well, but it's most specifically an Arrhenius base, right? So again, of course, all Arrhenius acids and bases are both Lewis and Bronsted-Lowry acids and bases. If it's an acid, an Arrhenius acid, it is also a Bronsted-Lowry and Lewis acid. But conversely, not all Lewis or Bronsted-Lowry acids are considered Arrhenius acids, right? That does get a little bit complicated. Luckily, for the purpose of the MCAT, as long as you can kind of predict what Arrhenius and Bronsted-Lowry acids look like, you're going to be fine. Basically, all of your Arrhenius bases are going to be easy to identify because they have hydroxide in them. All of your Arrhenius acids are going to be easy to identify because they're donating a hydrogen to solution. So I get why these definitions are really complex, but I'm basically just saying you don't really need to worry about them too much. Just be comfortable with the textbook definition of each and then just identify a simple example, because there are examples that get really complex out there, but don't worry about that. Just basic. If you can look at these examples that I've given you, you're going to be fine, essentially. So just to move forward to some other important things that we need to talk about with acids and bases. The first two definitions that we're going to talk about are amphoteric and polyprotic. So something that is amphoteric, it is a molecule that can either act as an acid or a base. These are molecules that can do both. Any of those definitions, Lewis, Bronsted-Lowry, Arrhenius, doesn't matter. They can do either. They can sometimes act as an acid. They can sometimes act as a base. I want to mention really quickly that this is not the same thing as amphipathic, similar prefix, but amphipathic is specifically having polar and nonpolar properties. This is like your fatty acids or the phospholipids that we see in the bilayer. Two different things. They're not the same thing. Amphoteric is talking about acids and bases. Amphipathic is talking about polarity. So just as an example, water is amphoteric, meaning that water, notice here that whenever water dissociates from itself, we can split one of these hydrogens off of the molecule. That hydrogen is released. So of course, that's going to be acting as an acid, a Bronsted-Lowry or an Arrhenius acid, but it's also releasing a hydroxide to solution as well. And so therefore it's acting as a base, right? So therefore water is amphoteric because it can do both. It can act as an acid or a base. The next word that we need to talk about is polyprotic. More accurately, I'm going to say polyvalent, because bases can't only sometimes are polyprotic, but everything is going to be polyvalent. So you'll probably see me use that definition or word a little bit more often, just to make sure that I'm covering all of the bases, not just acids. So these are molecules that have multiple what we call equivalents, where an equivalent is basically just the number of hydrogens or hydroxides that something can transfer. So for example, this acid right here, H2SO4, it has two equivalents because it has two hydrogens that it can donate, right? So therefore we would call it a polyprotic acid. Just to show you some examples, protic just generally means that it's something that can donate or accept hydrogens. Anytime we have like a protic solvent, it can donate or accept hydrogens. Protic molecules, same thing. So the polyprotic acids are specifically acids that have multiple hydrogens that they are donating to solution, essentially. You'll see that pretty much for the most part, we're going to be sticking with the Arrhenius and Bronsted-Lowry definitions of acids and bases. There's going to be one exception here in a few slides. But just FYI, like those are the two that you're going to be the most comfortable with on the MCAT because they're going to be by far the most common. Where conversely, HCl only has one hydrogen, so we say it's monoprotic. It is not polyprotic or polyvalent. It's the same word. So the bases are polyvalent, meaning that they can either accept multiple hydrogens or donate multiple hydroxides to solution, right? So just as some examples, notice that calcium hydroxide has two hydroxides that it can donate to solution. So we say it's polyvalent. This aluminum ion right here can basically accept multiple, it has donated multiple pairs of electrons, I should say. So because of that, we also say that it's polyvalent whenever it's involved in molecules. And then finally, we have sodium hydroxide, which is monovalent. It is not polyvalent. Notice that it only has one hydroxide that it can donate to solution. Right? Any questions about amphoteric or polyprotic? We're going to be revisiting polyprotic several times. We're going to bring up amphoteric again whenever we get to the conjugates. But this is a good stopping place for us to answer any questions about any of these definitions so far. Pretty simple. Polyprotic means it has multiple hydrogens or hydroxides. Amphoteric means it can act as either an acid or a base. So the next quality of an acid or base that we're going to talk about is conjugates, right? Like what the hell is a conjugate? So I'm going to define something really quickly. It's this word dissociation. So dissociation is basically just when a molecule splits up. And so like an acid, whenever an acid splits up, it's giving up its hydrogen, right? Like HCl here, it is dissociating into a hydrogen ion and a chloride ion. That's a dissociation. So the conjugate acids are specifically what a base is turning into after that dissociation has occurred. Right. And then, of course, like the other definitions of bases, like I said, we're mainly going to be talking through the Arrhenius definitions, but it's the same thing for the Lewis bases and as well as the Bronsted-Lowry bases. But like I said, mainly talking through Arrhenius because those are by far the most common. So just to show you an example of that, if we write the dissociation of NaOH, technically NaOH won't associate at all. We don't need to worry about that right now. But NaOH, of course, is going to be a base. It is dissociating into hydroxide and sodium, which is a conjugate acid. Because notice if we go the reverse direction, this sodium ion would essentially be accepting a hydroxide, which is the opposite of what a base does. So because of that, we call it a conjugate acid. A conjugate acid is what the base is turning into. So a conjugate base is just going to be the opposite. It's going to be what an acid turns into after dissociating, doing its dissociation reaction or accepting electrons, donating hydrogens, doesn't matter. Doesn't matter what definition you use. So for example, HF, whenever it dissociates, that means it's going to the right. And notice that we produce this fluoride ion here. So HF, of course, is the acid. That fluoride ion is the conjugate base, where if we go the opposite direction, it is accepting that hydrogen and acting as a base, a Bronsted-Lowry base, essentially. So that's what conjugates are. They are essentially just what the acids and bases turn into after dissociation. A base turns into a conjugate acid. A acid turns into a conjugate base, right? They come in pairs, essentially. So to kind of keep talking about this really quickly, a conjugate, if it's unstable, that thing that we're turning these things into, if that conjugate is unstable, it can do two things. It can either associate with other ions in the solution to stabilize itself because it's unstable. It doesn't want to exist in that conjugate form. The other thing that it can do is react with water. We're going to talk about that reacting with water here in a little bit. And we're going to talk about what it means to be stable here in a second as well. So, for example, looking at this molecule right here, this is called phosphoric acid, where we have the acid and its conjugate base, right? They come in pairs. The H2PO4 with a -1 charge is the conjugate base in this example. This H2PO4 is unstable. So because of that, it can stabilize itself through some sort of ionic interaction. It's got a negative charge right here, so it's going to be attracted to things with a positive charge. That can basically help stabilize that negative charge, make it a little bit easier for it to exist, right? Something that looks like this, where we're taking that H2PO4, maybe there's some potassium in the solution, and we form this molecule right here, where it's still that same conjugate base. It just now has formed what we call a salt. It's formed an interaction with this potassium ion. Any questions so far? Okay. So now more specifically, like I said, we're going to talk about that stability over the next few slides. We're going to talk about what a strong acid and base is. So these strong acids are acids that fully dissociate into their conjugates. And the strong bases are going to be doing the same. They are dissociating fully into their conjugate acids. So just as an example, if we look at HCl, whenever it dissociates, basically none of this HCl will exist anymore. It is going to entirely dissociate into that hydrogen ion and chloride ion. I'll get Dylan, I'll get to your question here in a minute. So because of that, because none of this HCl exists, this is a one directional arrow. We say that HCl is a strong acid. Anytime you hear the word strong acid, that's a textbook definition, meaning that it dissociates fully. One directional arrow. There's only a dissociation of that acid. So this conjugate base, I'm putting it in parentheses, basically because it can't really go backwards and act as a base. Like I said, there's no backwards arrow here. So it is such a weak base that it's not even really a base, essentially. And like I said, notice that the arrow is one directional, one direction down there, RIP Liam Payne. The arrow is one directional. So all of that HCl is going to be turned into product. There's not going to be, if I put HCl into water, there's not going to be any HCl that exists. It's going to dissociate into hydrogen ions and chloride ions. What drives a poly product to dissociate further? So usually you have to basically change the pH of a solution to convince it to dissociate further, if that makes sense. So while the first dissociation might be likely, the second and third dissociations might not be very likely. But if we basically remove a whole bunch of hydrogen ions from the solution, then that's going to drive that acid to dissociate more, if that makes sense. We're actually going to talk about that here in a little bit. We're going to revisit polyproducts whenever we get to the whole topic on pKa and Ka and stuff like that. That will make more sense here in a little bit whenever we get to a further discussion of how polyproducts work, essentially. So then just as an example of the strong base, for example, we have sodium hydroxide that is only going to dissociate into this sodium ion. So the sodium hydroxide, we call it a strong base. The sodium ion, we technically call it a conjugate acid, but I have acid in parentheses because it is such a weak acid that it's literally inert. It doesn't react with anything. It's really stable on its own. It's not even going to go backwards to form any NaOH. It's incredibly stable. It's really happy to be that way. Right. And like I said, like I've been talking about, there's going to be one exception, but pretty much from here on out, we're mainly going to be using the Arrhenius definition. If that helps you identify Arrhenius acids and bases, we're mainly going to be using the Arrhenius definition. And then, like I said, remember that if I don't specify the state of matter, you can just assume it's aqueous. So they're conjugates in the original acids. Everything here is aqueous. Right? So basically, just to put this in another way, the strong acids and bases are incredibly strong. They dissociate fully because of how stable their products are. Their products are incredibly low in energy. They're incredibly stable. They're incredibly happy to exist in this form. that they have no reason to turn into anything else. They have no reason to go backwards and reform that initial acid. That's why the strong acids and bases are strong, essentially. This is going to be an idea that's reiterated here in a second when we get to the weak acids and bases. So there's 6 strong acids that you need to memorize. For the MCAT, you need to be able to basically just identify these out of a lineup. And there's 8 strong bases that you need to identify. So the 6 strong acids, I'm going to break them up into 2 groups. Basically, it's the heavier halogens with hydrogen, right? So we have hydrochloric acid, hydrobromic acid, and hydroiodic acid. Notice that fluorine is the most electronegative atom. So you might be surprised if like, well, why is fluorine not on this list? Hydrofluoric acid, like, why is that not a strong acid? Fluorine loves electrons. So what's wrong with that? Remember that we're talking about stability here. So even though fluorine really wants those electrons, as soon as it receives those electrons and has a negative charge, it's too small to hold that negative charge. So it gets a little bit unstable and it's going to go back and reform some of that initial acid. So because of that, HF is a weak acid. Kind of surprising, but basically, like I said, when you think about stability, this makes more sense. That ion that we're forming, that conjugate base, when we're talking about the acids, needs to be incredibly stable. So stable with that charge that it doesn't want to go backwards at all. There's other strong acids. There's 3 other ones. There's sulfuric acid, there's perchloric acid, and then hydroiodic. That's not supposed to say hydroiodic acid. That is supposed to be, yeah, of course. That's supposed to be nitric acid. Let me fix. So just to pull up that list again, is there a way to? Not particularly, because one of the things that's frustrating about these other acids is that there's very similar looking acids. For example, there's what's called chloric acid, which is HClO3. So it looks very similar. There is a naming convention that makes it easier to identify perchloric versus chloric. But unfortunately, outside of repetition, there's not necessarily an easy way to memorize these 3 acids on the right. The every single other strong acid and the strong bases as well, they're going to be really easy to memorize. But these 3 are the ones that I kind of just recommend having in your flashcards, just regurgitating essentially. So now to talk about the strong bases, I have them colored wrong. You'll start noticing that everything that's basic is going to be in blue. Everything that's acidic is going to be in kind of like a reddish pink. That's I carefully chose that color, as you'll see whenever we get to litmus papers why that's the case. But I forgot to color these blue, so sorry about that if you've been catching on to the color coordination scheme. But so there's 8 strong bases. If you look at the periodic table, basically, if you take all of those group 1 metals and add a hydroxide molecule to them, they're going to be strong bases. So lithium through cesium and then add a hydroxide, those are the strong bases. Ignore francium because things get weird when you get to the bottom of the periodic table. But lithium through cesium with hydroxide, those are the strong bases. 5 of the 8. The other 3 are the heavier group 2 metals. So calcium through barium, because those metals prefer to have a +2 charge, they're going to be taking on 2 hydroxide ions, which is why we see barium with 2 hydroxides, strontium with 2 hydroxides, and calcium with 2 hydroxides. So you can identify those strong bases really easily just by looking at the list, looking at the periodic table and knowing lithium through cesium with hydroxide, calcium through barium with hydroxide. And the heavier thing is the exact same logic as the halogens from earlier. Because they're heavier, that means they're larger and they're much more easily able to accommodate weird charges that they might be taking on, a +1 or +2 charge. That's why the smaller group 2 metals don't exist as like magnesium. Magnesium is not a strong base. Okay. So now to talk about weak acids and bases, the opposite of strong acids and bases. The strong ones we're dissociating fully. The weak ones are only dissociating partially into their conjugates, right? So weak acids are dissociating partially into their conjugate base. The weak bases are dissociating partially into their conjugate acids. So just to show you like another example, HF, like we talked about before, this is a weak acid because this fluoride ion, the conjugate base, is not incredibly, it is unstable on its own. It is going to be slightly basic, meaning that it has to kind of go backwards a little bit, run this reaction in the reverse direction, in order to reform some of that initial hydrofluoric acid. So just to kind of put this in a different way, if I put HF into water, there's going to be some HF that's left over. It's not all going to dissociate. Some of it's going to dissociate and then come right back and reform that initial HF, right? It's a weak acid. It has a conjugate base that's unstable. That's why it's a weak acid. Conjugate bases, just as another example, if we take beryllium hydroxide, that beryllium is a weak base because this conjugate acid is unstable. It's going to do a little bit of this reverse reaction, that association reaction, in order to reform some of that initial base. So strong acids and bases, they dissociate fully. Once you put that acid and base into water, it doesn't exist anymore. The weak acids and bases, there's going to be a little bit of bidirectionality there, right? Like notice that all of these arrows are bidirectional. They go both ways, right? Not unidirectional. So just to make this easier, there's not a list of weak acids and bases you need to memorize. Literally anything that's not on that previous list we just looked at. Anything that's not on that list, you can consider weak. If it's on that list that we just looked at on that other slide, it is strong. Everything else is weak, if that makes things more simple. So for example, like carboxylic acids. If you know anything about OChem, sometimes people think carboxylic acids are strong. They are not strong. They are just relatively strong. Carboxylic acids are still considered weak acids because they do not dissociate fully, but they are just stronger than some of the other types of acids that we have, meaning they're more likely to dissociate, but they are not strong, right? So just make sure that you're keeping that difference between strong versus stronger in your head. Strong, literally textbook definition, meaning it dissociates fully. Everything else is weak. And so, of course, within there's going to be some weak acids that are stronger than other weak acids. Same thing for the bases. But if it's not on that list, it's weak. So, to kind of reiterate this idea, we're going to bring up salts really quickly. This is one of those topics that confuses a pretty large number of my students over the years. So a salt is simply a metal with a non-metal component. There's a few exceptions to that, but pretty much every single salt you see on the MCAT, there's going to be some sort of metal with a group of non-metals. Could be 1, could be 15, doesn't matter. Metal plus non-metal, that's a salt. So salts are solids, like for example, NaCl, that sodium chloride that you have in your pantry, that is an ionic solid. Unless you put it in water, then some of that salt can dissociate into ions, right? Just put a different way, like basically whenever you put salts into water, that salt dissociates, breaks up into a metal cation and a non-metal anion. Just to kind of show you what that looks like, this is sodium chloride, that thing that contributes to high blood pressure. I mean, salt's awesome, but basically sodium chloride, whenever you put it into water, this salt is going to dissociate into a sodium ion, a cation because it's positively charged, and a chloride ion, an anion because it's negatively charged, right? So if these ions in these salts are unstable after this dissociation has occurred, they're going to react with water to stabilize themselves. Right? Just to show you an example, like so if you have a salt that dissociates into a stable cation and an unstable anion, this unstable anion can then react with a hydrogen ion from water to form a more stable molecule. It can pull hydrogen concentration out of water to form a more stable molecule, right? We're going to go through some examples of this here in a second. But basically, the idea here is if it's a stable ion, which that's knowing the strong acids and bases, that's going to really help us here. But if it is a stable ion, it's fine. It's neutral. It's not going to react with water at all. If it is an unstable ion in that salt, then it's going to react with water in some way. So just the next question that you might be thinking is like, what do you mean by stable versus unstable ions, right? I know we've kind of talked about that with strong versus weak acids, right? Strong acids have very stable conjugate base ions. Weak acids have very unstable conjugate base ions as well, right? So basically, just to kind of explain how this works, the exact reason that strong acids and bases are strong is the exact reason for why some ions are going to be stable, right? The strong acids are strong because the ions they dissociate into are incredibly stable. like I said, that this will make more sense as soon as I kind of explain some of the examples. So, like I said, strong acids and bases are strong because of how stable their conjugate ions are. So, if a salt contains the conjugate ion of one of these strong acids and bases, basically, if you memorize that list of strong acids and bases and you see an ion that's in that list, that ion is stable and it's not going to react with water. If you see a salt that has some sort of ion, some sort of part of the molecule that is not on that list, meaning it came from a weak acid or base, that ion is unstable and it's going to turn around and react with water. So, for example, magnesium chloride. So, magnesium chloride, whenever it dissociates into a magnesium ion and some chloride ions. So, we're going to start with these chloride ions because HCl, that is a strong acid, right? Meaning that the chloride ion, Cl minus on its own, is very stable. So, if it's stable, it has no reason to react with water at all. So, therefore, it's going to be kind of neutral. It's not going to do anything, right? But Mg2 plus, it does not show up any of our strong acids or bases, which therefore means that that ion is unstable. This Mg2 plus is unstable. It is a conjugate acid of a weak base. So it's a little bit unstable. And because of that, we're going to see it start to interact with water. So because it has a positive charge, that's going to be the easiest way to know what it's doing. If it has a positive charge, that means it is going to be reacting with a negatively charged thing. Water is made up of a hydrogen ion and a hydroxide ion. Hydrogen ion is positively charged, hydroxide ion is negatively charged. So since magnesium 2 plus is a cation that is unstable, it is going to interact with the anionic hydroxide from water, right? Therefore, forming a little bit of magnesium hydroxide, technically it could accept another one to form MgOH2 if it wanted to, it doesn't matter. But it is pulling hydroxide out of water. We'll talk about what that means here in a second. Right? So basically, if the ion doesn't show up in any of the strong acids or bases, that means it's weak or unstable and it's going to react with water. Right? Any questions about how to identify what ions are stable versus unstable, right? If you just memorize that list of strong acids and bases and what they dissociate into, you're going to be perfectly fine for what we're talking about here. So that's the advantage of like having those notes up in front of you, is you can just quickly scroll up to that list. So just to kind of talk about this a little bit more, we're going to start doing some examples, right? So the first example that we're going to talk about is copper chlorate. I think that's what this ion's called. I don't know. I'm struggling with what this is called. So whenever copper chlorate, it is a salt because it is a cation metal with an anionic portion, all this non-metal stuff over here. So whenever you put it into water, it's going to dissociate into that metal, which is going to be cationic. And then all of the non-metal stuff is going to stick together as an anion, right? So copper, this is the only one that I'll have you guys participate in a little bit. Like again, no pressure at all. But is copper stable or unstable? Do we see copper in any of those strong bases or acids, or do we not see it? Somebody. So we do not see copper in any of the strong bases or acids. So because we don't see copper in any of those strong bases or acids, that means copper is unstable on its own and it has to react with water in some way, right? So copper is going to be unstable, but this chlorate ion is stable. Like in perchloric acid, it's HClO4. So that means that this one's really stable and it has no reason to react with water, right? So this copper that's unstable, it's going to satisfy this charge that it has. It's going to accept a hydroxide to form CuOH. So if we are removing, that hydroxide is coming from water. If we are removing OH from water, that water is becoming more acidic. So because of that, we say that copper chlorate is an acidic salt because it's an unstable cation that's going to react with water, pulling that hydroxide out, with a stable anion that's not going to touch the water at all. Just as another example, sorry, my cat's behind me. He's really bugging me today. Just as another example, we have sodium carbonate here, right? Sodium carbonate it dissociates into 2 sodium ions and 3 carbon and a carbonate ion. So the sodium ion, of course, NaOH is a strong base, which means that this sodium ion is stable, right? It's stable on its own, which is why NaOH is a strong base, right? But this carbonate ion does not show up in any of those strong acids and bases. So because of that, it's unstable and going to react with water in some way, right? It's going to satisfy this charge. It has a negative charge. So it's going to be pulling these hydrogen ions out of that water to form what's called bicarbonate. It could technically do it another time to form H2CO3. That's called carbonic acid, but you don't need to worry about that. So anytime we are removing hydrogens from water, that's what bases do, right? So if we are removing hydrogens from water, the solution is becoming more basic. So because of that, we would call this sodium carbonate salt a basic salt because it has a stable cation that has no reason to interact with water, but an unstable anion that is going to be pulling hydrogen ions out of water. One final example, let's look at strontium bromide. So when strontium bromide dissociates in water, it forms a strontium ion. This is supposed to be 2 plus right here. That's a typo. That's my bad. Strontium ion with 2 bromide ions. So strontium shows up in one of our strong bases, right? Strontium hydroxide. So perfect. So because of that, it is stable, right? Has no reason to react with anything. What about bromine? Does bromine show up in any of our strong acids or bases? Check the list of strong acids in the halogens. So HBr, yeah, HBr is a strong acid. It's in that list. So because HBr is a strong acid, that means that bromide ion that it's dissociating into is incredibly stable. Both of these ions are incredibly stable on their own. That's why those acids and bases are strong. It's because of how stable these ions are. So whenever we start putting them together in salts, that's how we can start predicting if they're going to interact with water or not, how we know if it's going to be an acidic or basic salt. So we have 2 stable ions here. They have no reason to interact with water. And so we would call this a neutral salt because both of the ions that we're forming are both stable. Like for example, sodium chloride, NaCl, those are both stable ions. Na plus is a stable ion. Chloride Cl minus is a stable ion. Therefore, that's how we know that, like, if you were to test the pH of NaCl, it's neutral. It's not acidic or basic. So basically, just I'm hoping that that's a significantly easier way to identify the acidic and basic salts. You're just looking for the conjugates of weak acids and bases. Those are the ones that are going to be interacting with water. Right? Okay. Any questions so far? Okay. All right. So we're going to take our first short little break here. This one's just going to be a short 5-minute break, and I will be back at 10 after the hour. Right. I'll be right back. I'll see you guys in a minute. All right. I am back. I'll give you guys just a few seconds to kind of trickle back in. But like I said, really appreciate you guys being here. Glad I could get like my free lecture series up and running. But like I said, especially because this is a decently long lecture, do not feel bad at all about having to leave. Like I said, even if I end up being the only one here, I'm still gonna truck out the whole thing, finish out the whole lecture, just so that so I can send it out as a recording. Obviously, the more people we have, the more questions I can get just to clarify things. Because even if you think you have a question that maybe only you have, I think you'd be surprised a lot of people have a lot of the same questions. So that's why it's definitely good to have other people giving me feedback and asking me to clarify things. Because I'm sure if you have a question, I'm sure someone else who, even like the few dozens of people who are going to be watching this recording, they're also going to have that same question. So I really appreciate you guys being here. But we are going to move forward. We're going to quickly talk about what are called neutralization reactions. So a neutralization is anytime you combine an acid and a base. And what this does is this causes the formation of water and a salt molecule, right? Anytime you add an acid and a base together at the same time, you form water and salt, right? Just to kind of show you how this works. Basically, like, let's just start off by talking about what acids and bases do, right? we're going to talk through Arrhenius acids and bases. The acid is going to donate hydrogen ions. The base is going to donate hydroxide, right? So whenever we put HCl, which is an acid, and NaOH, which is a base, into water, they're going to dissociate into the hydrogen and hydroxide ions, as well as their respective conjugate base and conjugate acid ions, right? Which are, remember, like we just talked about, they're incredibly stable because they're from the strong acids and bases. So they're not going to react with water at all. So the hydrogen ions and hydroxide ions can basically just combine with each other. They can just cancel each other out at this point, forming just a liquid water molecule at this point. And then from here, these ions, they're stable. They don't need to react with anything, but they can still just have a positive and a negative charge. They can just interact with each other if they really wanted to form a salt, right? Where notice this new thing here that happened is we basically just put these two things together and we can form a solid salt. You don't need to worry about the state of matter that we're forming here. Solid would be like a precipitate of salt. Aqueous would be the ions separated from each other. You don't need to worry about that. That goes into like solubility rules of NaCl, stuff like that. Basically, for our purposes right now, for acids and bases, you just need to understand that we can make a salt using a neutralization reaction. Basically, anytime you add an acid and a base together, they cancel each other out. One important thing that I want to know, especially for whenever we get to math, is that the thing that you need to make sure is equal is the number of moles that these two things are producing. In order for this cancellation, this neutralization to happen properly, you need the same number of moles of HCl as you do moles of NaOH. That way, the number of hydroxides and number of chloride ions is the same. If you have different concentrations and different molarities, maybe if you have more hydrochloric acid than you do sodium hydroxide, the solution is going to be a little bit acidic, right? There will be some semblance of a neutralization reaction, but you're going to end up with an acidic solution because there's excess HCl, right? So basically, in order to make sure that these neutralizations happen and then stop whenever they're done, you're looking at the number of moles, right? We'll talk about that. We'll revisit that a little bit later. Whenever we get to titrations, especially. And then, like I said, just another reminder, if I have not specified a state of matter, you can just assume it's aqueous, right? Like I said, I'm lazy. I'm my own boss at this point. I can add and do whatever I want at this point. And I get lazy with adding the states of matter. It's a few more characters that I'm just too lazy to type out. So the next few things that we get to talk about are usually brought up whenever we talk about salts. But kind of like we just talked about with salts, like usually that's a solubility topic, right? But salts can be acidic and basic, which is why I want to talk about it here, right? So we're going to be talking about complex ions. So complex ions is a complex ion. It's also called a coordination complex, as you can see there. It's a molecule that has a central metal cation, has a it has a metal cation that's basically in the middle. It's most commonly a transition metal that is going to be covalently, not ionically, covalently bonded to multiple what we call ligands. These are going to be anions. And once they form these covalent bonds, we call these covalent bonds coordinate covalent bonds. So just to make this make sense, I'll show you an example here. There's something called coordination number. That's just the number of covalent bonds that were formed. I'll talk about that here in a second. But looking at an example is going to make this the easiest to understand, right? So here's the molecule heme, which makes up hemoglobin, right? Which is really important for carrying oxygen. So heme is a complex ion, where notice we have a transition metal that's in the middle here that is surrounded by some sort of ligand, right? That's going to be donating electrons to this cation, this transition metal cation. So heme is made up of iron. This iron is the metal cation. It is going to be, since it's in its cationic form, it is going to be accepting electrons from the ligand. It's accepting electrons, right? And if you guys are here, remember what type of molecule accepts electrons. Is that a Lewis acid or a Lewis base? If it accepts electrons, right, it's a Lewis acid. If it accepts electrons, that means it's also donating hydrogens. I think most people understand donating hydrogens as acids. But whatever it's doing with hydrogens, it's doing the opposite with electrons. If it's donating hydrogens, it's accepting electrons. So this metal cation is going to be the thing that's acting as a Lewis acid. This is one of the last times we're going to be talking about Lewis acids today. And it combines with the ligand, which is going to be donating electrons and therefore acting as a Lewis base. So, for example, in heme, we take this iron cation, and it is going to be receiving electrons from these nitrogens in order to form these coordinate covalent bonds here. And notice that there's 4 of these covalent bonds here, so this molecule's coordination number would be 4. That's not really something that's important for us, right? But just as another example, this is another place that acids and bases show up. It's technically like a salt solutions thing, solubility thing, but we have some Lewis acid and base chemistry going on here. The metal cation is going to be a Lewis acid. The yeah, it's Fe2, not Fe3. That's what this number right here says. It's oxidation state Fe2 plus. Which I mean, that gets really complex with understanding how does it have a +2 charge? How does it accept electrons and coordinate covalent bonds? Because we're like covalent bonds with metals is a very weird thing. Like that's something that on the MCAT you're only going to see with these complex ions. Every other time you see a metal, it's going to be an ionic bond. But yeah, that's what the 2 means. But yeah, basically, the Lewis acid is going to be the metal cation. It is accepting electrons because it's cationic, so it has a positive charge. It can accept electrons. This is called a porphyrin ring. The other part of heme, it is donating electrons to this iron molecule to form the complex ion. So that's the basic makeup of a complex ion. We're going to keep talking through the basically, because we talked about the basis of complex ions, but we're going to talk about what they can do, right? So they themselves can act as an acid or a base, but they can also increase the solubility of other salts and therefore increase that salt's acidity or basicity, right? And so let me explain what I mean by that, right? We're going to use a really basic analogy where imagine there's this bucket and all you can put into the bucket is 5 red balls and 4 blue balls, right? That's it. That's all you can fit, right? This is kind of like the imagination of like, this is how much acid can dissociate or how much salt can dissolve. This is the maximum number, right? You have thrown 5 red balls and 4 blue balls. But now imagine someone comes by and they start pulling some of these red balls out, right? So now it kind of looks like this. You have still thrown those 3 balls. It's just they're no longer in that box. So now you can keep adding more balls into that space, right? There's a little bit of empty space that you can keep adding balls. So if we total up all of the balls that you have thrown into this bucket, it is actually a larger number than it was before. You initially only started off with 5 red balls and 4 blue balls. But now, since something is removing some of these red balls from that solution, from that container, you now can put in a larger number of balls, right? It's basically this idea that complex ions can start removing some of these ions from solution to allow more of that salt or acid to dissolve, right? So let's look through like an actual real world example, right? So, like I said, they themselves, complex ions, we just talked about how they can be a Lewis acid or base. But because they can increase the solubility of another salt, they can increase that salt's acidity or basicity if it's acidic or basic, right? Obviously, if it's a neutral salt, that doesn't help it at all when we're talking about acidic and basic. But for example, if we take sodium chloride and dissolve it into water, and then we add copper sulfate. I added a clarification here that like copper likes to form 4 coordinate covalent bonds with ammonia, right? Just basically telling you that we're going to be forming a coordinate covalent bond here. The question is just asking what happens to the acidity or basicity of that solution, of that salt, right? So let's start with the, this is supposed to be, say, NaF right here. That's my bad. Another typo, sorry. If we add that NaF to water, it is going to associate into that sodium ion and the fluoride ion. And just as a remember, like we talked about earlier, this sodium ion is involved in a strong acid or base, specifically NaOH, which is a strong base. So because of that, it is really stable. It has no reason to interact with water at all. It's inert, it's stable, it's neutral. It's not going to do anything. This fluoride ion, we do not see it in any of those strong acids or bases, which also means that it is unstable. And since it's unstable, it's going to neutralize this charge that it has growing and pull hydrogens out of solution. It's acting as a Bronsted-Lowry base. So in doing so, it is a basic salt. This NaF right here is a basic salt, right? That's part one. Then the question also says we're going to be adding this copper sulfate, right? So let's write out what happens with copper sulfate. So it's dissociating the copper ions, which we know are unstable, and sulfate ions, which are stable, right? Like H2SO4, that's one of our strong acids. So this SO4 ion is incredibly stable. Technically, it's a little bit more complex than that. H2SO4 is a little bit weird as a polyprotic strong acid. You don't need to worry about that for the purposes of the MCAT. So this copper ion, like we talked about, is unstable. It does not show up in any of those strong acids or bases. So it's going to basically just react in any way that it can. Like technically, it can sort of react with water a little bit. But the main thing that it's going to do is start forming a coordination complex with some sort of anion, right? And notice that we have another unstable anion right here. We have an unstable cation and an unstable anion. So because of that, those two unstable things are probably going to interact with each other. That's what we see happens, right? That copper ion and that fluoride ion are going to basically form a salt. Again, you don't need to worry about if it's solid or aqueous. To basically stabilize that charge that those unstable charges that these two things have, right? So because of that, we are removing this fluoride ion from solution. We are decreasing this concentration right here in this first reaction. And so because of that, this reaction can shift to the right again. Le Chatelier's principles, right? If you remove a product, that reaction will shift towards the products. So basically, by adding a complex ion, that complex ion can pull ions out of solution. And if those ions are involved in an acidic or basic salt, we just made that salt more acidic or basic, depending on whatever it is. So we just made this basic salt a more, we allowed more of that salt to dissolve. And so because of that, it's going to be a much stronger base. We're going to be able to pull more of those hydrogen ions out of solution, right? Long story short, complex ions, they themselves can act as Lewis acids and bases, but additionally what they can do is if we add them to another solution of salts, they can make those salts more soluble and therefore more acidic or basic, right? Complex ions increase acidity or basicity. This is going to be summarized here in a few slides. So the next kind of complex thing that we need to talk about is what's called the common ion effect. Again, if you've studied solubility, this probably looks familiar. This is something that's talked about in solubility. But so the common ion effect is basically this idea that if you have two different species, two different salts, for example, that are trying to produce the exact same thing, since they're trying to produce the same thing and fit it into the same container, there's less of a drive for that to actually happen. For that to actually happen. Right? I'll get to that in a second, Dylan. There's less of a drive for that to actually happen. And just like make this much more simple, the salts are going to become less soluble because they're trying to put the same thing into solution. So when we're talking about acidic and basic salts, those are going to dissociate less. The common ion effect, which is not the same thing as complex ions, two different words, entirely different ideas. The common ion effect is going to decrease acidity and basicity of a salt. If F is bonded to copper and not OH, why is it more basic? Yeah, I'll scroll back to the slide really quickly. So because this F right here, if it's binding to copper, like that itself doesn't really have anything to do with acidity or basicity, right? Like copper is not involved in acidity or basicity or anything. But what this is doing is this is causing this reaction right here to shift further to the right. We are allowing more of this fluoride ion to dissolve. We're allowing more of this salt to dissolve because as this reaction happens right here, it is removing this fluoride ion and shifting this reaction to the right. And this is a basic salt, meaning that whenever it dissolves, it is allowing more of this fluoride ion either to interact with the copper. It can still interact with the copper, but more of it can start pulling hydrogens out of that solution. It has the choice, basically. And we're just giving more fluoride ions that choice. Does that explain your question? It's not necessarily this reaction right here that's acidic or basic. It's that we are allowing this reaction right here to accelerate. Yeah, okay, perfect. Yeah, good question. Okay. So just going back to what we're talking about, the common ion effect, it's basically the opposite idea of what's happening. Instead of removing ions from solution, we have two salts that are trying to put the same ion into the solution. So I have another really simple example, right? We're going to talk about like shirts. So just imagine that you and your friend, you both have 5 red and 5 blue shirts, right? I have 5 red and blue. Dylan has 5 red and blue, right? So we are both, there's one bucket in front of us that can hold 10 shirts, 5 red and 5 blue. If we are both trying to put shirts into that bin, neither of us are going to be able to put all 10 of our shirts into that bin, right? That bin can only hold 10 shirts. That solution can only hold a certain number of ions. So because of that, neither of us are going to be able to get all 10 of our shirts in, right? That's basically what's going on with the common ion effect. We are seeing this idea that because you and I are both contributing the same thing to a solution, neither of us are going to be able to contribute as much, right? That's what the common ion effect is. That solution can only hold a certain number of shirts. And if we're both trying to put shirts in there, we're both going to max ourselves out faster. Like maybe I can only get in 3 red shirts and 2 blue shirts, and Dylan can get in 3 blue shirts and 2 red shirts, something like that. Neither of us got in our full 10 shirts, right? That's what the common ion effect is. There's less salt dissolution, less salt breaking up because that ion is being saturated. There's too much of that ion. You have a competitor, essentially. One thing that I want to add, this is not at all important for acid-base chemistry, but one thing, since we're already here, the other thing that I want to add is that the solubility of both salts is going to decrease. The likelihood that both salts is going to decrease, but more specifically, the less soluble salt is going to see a bigger decrease. So, for example, if I'm worse at putting shirts in than Dylan, I'm going to suffer way more than Dylan is. Dylan will still not be able to get all of his shirts in, but I'm going to see a bigger decrease in the number of shirts that I can put in. Where if I'm not even there, Dylan can put all 10 shirts in. But the second I'm there, maybe Dylan can only put in 8 shirts, but I'm only able to put in 2. Right? That's what the common ion effect is, right? It's not allowing those salts to dissolve. So just to put this simply, for basically what you need to know for the MCAT, right? We're going to talk about how this affects acidity and basicity, which we already kind of described. The TLDR is on the next slide. Sorry, I was getting ahead of myself. So again, we're going to talk again really quickly. Another review. What makes a salt acidic or basic, right? It's what's happening with that ion after dissolution. If that salt has an unstable ion, that ion is going to interact with water. And remember, the way that we predict that ion's stability is whether or not it's in one of the strong acids or bases. If it's in one of the strong acids or bases, it's really stable. It does not need to react with water. If it's not, if it's a weak conjugate acid or base, that means it's going to have to react with water in some way. So, like I said, this example that we talked about earlier, this Na ion right here is stable, doesn't need to react with water. NaOH is a strong base. This fluoride ion is unstable, so it's going to pull hydrogen ions out of water, and therefore it's a basic salt. The common ion effect is going to decrease how soluble this salt is, how much dissolution is going to happen, and therefore there's going to be less amount of this fluoride ion, right? So for example, if I add calcium fluoride to the same solution, both of these salts, sodium fluoride and calcium fluoride, are both contributing fluoride to the same solution. That solution can only hold a certain amount of fluoride, so there's going to be less dissolution of this salt and less dissolution of this salt as well. Less dissociation, whatever word you want to use. Both of these salts are going to see a decrease in how much of that salt can dissolve, essentially. So because of that, we just made this sodium fluoride a less basic salt. Not only did we make it less soluble, we made it less basic. Because in order to be basic, this fluoride ion has to be on its own. But the common ion effect is preventing that from happening. It's preventing this arrow right here from going to the right. Right? So long story short, the common ion effect decreases solubility and decreases the acidity and basicity of salts. But that's the take-home message. Realistically, this next slide that we're about to talk about here is the TLDR. Like essentially, you don't really need to understand why all that stuff is the case. I personally think that significantly helps understanding why that stuff happens. But realistically, for the MCAT, if you just understand that complex ions are going to increase solubility and therefore increase acidity and basicity of salts, common ion effect is going to do the opposite. You're going to be fine. Right? Any questions about that so far? About complex ions and the common ion effect? Okay. All right. With that being said, we're going to talk about K, not like potassium necessarily. I threw up like a stupid picture here, but we're going to talk about what K is, right? So K is what we call an equilibrium constant, specifically KEQ. Basically, it is the ratio of products to reactants at equilibrium, right? One thing I want to add really quickly is that when we're calculating this, you need to exclude solids and liquids. Do not include solids and liquids in these KEQ values. Right. That's why, like, whenever, if you know what the KSP is, that's the K value for salts. We only include the dissolved ions because they're aqueous. We do not include the salt itself because it's solid. Right. But basically, KEQ, all of these equilibrium constants, there's two that we're going to talk about here. It is just a ratio of products over reactants. So for acids and bases, there's basically two types of K, subtypes, essentially. They're still products over reactants, but they're specific to acids dissociating and bases dissociating. So for example, for an acid dissociation that looks like this, if we just take the concentration of products, remember everything is aqueous here, so we're going to include everything. We just take the concentrations of the products and put it over the concentrations of the reactant here. It basically looks like this right here. That's what our Ka is. That's what we call it. It's the acid dissociation constant. It's a lowercase a. Right? This is just telling you how good an acid is at dissociating. We're going to kind of talk about that on the next slide. For a base, whenever we talk about the dissociation of a base, it's pretty much the exact same idea, but instead of using hydrogen ions, we're talking about hydroxide here. Because remember, like I talked about earlier, we're mainly looking at Arrhenius acids and bases now at this point. So whenever we write the base dissociation constant, this is abbreviated as Kb, notice that we now have hydroxide up here, right? Instead of the hydrogen ions. And we've swapped out the conjugate base and acid with a conjugate acid and base. So it's just products over reactants. You just need to know that for bases, we're going to have a conjugate acid and hydroxide in the numerator. For acids, the Ka value, we're going to have a hydrogen ion and a conjugate base in the numerator, right? It wouldn't make any sense for there to be any hydroxide here in the Ka value because acids don't make hydroxide. They don't release hydroxide. So just to kind of expand on this a little bit, these acid and base dissociation constants. So if those K values are increasing, that means there's more products, right? Because it's products over reactants. So because of that, that means there's more acid dissociation occurring, right? Then the same logic is going to apply to bases and Kb as well. So because of that, a higher Ka means a stronger acid. That acid is more acidic than some other acid that you're looking at. A higher Kb means it's a stronger base. Right? All of this logic that we're talking about with Ka and B is going to be the same thing. It's just one we're talking about acids, the other one we're talking about bases. So just as an example, they could ask you the question of like which acid is going to be producing a stronger hydrogen concentration, producing more hydrogens when we put it into water. So the two examples that I gave is acetic acid or hydrochloric acid, right? So notice that this Ka is 1.75 times 10 to the negative fifth. This is 1 times 10 to the sixth, right? Remember that these are ratios of products to reactants, right? It's going to be HCl. HCl's Ka is significantly, if I put the Ka up, notice that basically in order to calculate this number right here, the higher this numerator is, the stronger the acid, because this numerator has hydrogen ions on it, right? The higher this Ka value is, the stronger the acid is, like we talked about right here, right? So because HCl has a much higher Ka value, like that's ridiculously high. You'll see when this correlates to pH. If you know what the pH scale is, it's usually 0 to 14. This correlates with a pH of around -5, -6. It's so acidic that it's kind of off our usual scale. Whereas this one's kind of around 5, pH of like 4.8, something like that. So basically, because of that, HCl is significantly more acidic. It's going to produce a way larger amount of hydrogen ions, right? So the higher the Ka, the stronger the acid. The higher the Kb, the stronger the base, right? If you have any questions, feel free to send them in at any point. So we're specifically going to kind of start connecting this to some of the other math that you're going to have to do on the MCAT. And so the first thing that we need to talk about is what's called the auto-ionization of water, right? So water, is water amphoteric? Someone remind me, someone who was here earlier in lecture, is water amphoteric? That word, can water act as an acid or a base? Can it choose? Anyone remember? Tell the K. Yeah, it can, right? Just to show up that picture that we talked about earlier. Water can act as an acid, meaning it's producing hydrogen ions in solution. It can also act as a base, meaning it can produce hydroxide in solution, from when we talked about that in the first hour. So if I were to write the KEQ of this reaction, we're going to call it the KW. It's a specific subtype. We're going to leave out the water because it's a liquid and we don't include liquids. It's basically just the hydrogen concentration versus the hydroxide concentration. And so for pure water at 25 degrees, this actually is a constant value. This auto-ionization of water is always equal to 1 times 10 to the negative 14th. So this is one of those things that I recommend memorizing. That KW is equal to 1 times 10 to the negative 14th, right? If it's in your notes, basically. I also have like abbreviated notes linked to my content depth guide. Basically, that stuff that's mentioned, this is like stuff I'm especially saying to recognize and memorize. I'll have all of the equations as they start showing up boxed in at some point. You'll see that here in a second. So another thing to point out really quickly is you might see hydrogen ions replaced with what's called the hydronium ion. They're the same thing. It's the exact same thing. You can treat them interchangeably. Don't worry about that. Most of the time you're going to see hydrogen ions, but just know that they're the exact same thing. So in pure water, there's an equal amount of hydrogen ions as there is hydroxide ions. So because of that, we can just calculate what the concentration of each of these two things is going to be using this constant for water. And we just divide it by 2 essentially. So because of that, the hydrogen in pure water at 25 degrees Celsius, the hydrogen concentration is going to be 1 times 10 to the negative 7th, which is the exact same thing as the Ka of water. That's like if water acts as an acid, its Ka is 1 times 10 to the negative 7th. For hydroxide, it's the exact same number. 1 times 10 to the negative 7th, that's the Kb of pure water. So because of this, basically it sets up this relationship where anytime we multiply the Ka of an acid times the Kb of its conjugate base, or in this example, water as an acid, water as a base, it is always going to equal 1 times 10 to the negative 14th at 25 degrees. I'll make a comment on this on the next slide, but you can just always assume it's 25 degrees unless you're told differently, right? So this is the first like actual real equation that you pretty much need to memorize, right? We get it from this Kw value. This number is constant. And because it's based on the hydrogen concentration and the hydroxide concentration, which directly correlates with the Ka and Kb, we know that multiplying Ka times Kb is always going to give us this number right here, unless we change the temperature. We're going to talk about that here in a second. Right? Basically just showing you how we get to this equation. As soon as you memorize this equation, you're fine. Okay, with that being said, what happens if we change the temperature, right? Because temperature is not always constant. Maybe they're going to throw that at you. So just to throw this up again here, if you increase the temperature, there's going to be more water ionization. The reason for this is an endothermic process. So like heat is like a reactant, if that makes sense. So if you're heating it, increasing the temperature, that means you are adding more reactant, and this reaction is going to shift to the right. Right? There's more water ionization. Increasing temperature means that we're going to have more products. So if there's more water ionization, there's more products, and that means our Kw is going to increase, right? So because of this, Kw increases with increased temperatures. Kw decreases with decreased temperatures. This is one of those things that you're not necessarily going to need to calculate, but you do need to understand conceptually that Kw number, that 1 times 10 to the negative 14th, is dependent on temperature, because it's a constant that depends on the temperature of the solution, right? Like I mentioned earlier, you can assume that it's at 25 degrees unless you're told differently. But basically, that's one of the first important things that we need to talk about really quickly, kind of like the one-off content things that you need to know for the MCAT. KW, it's going to increase with increased temperatures. It can decrease with decreased temperatures. We're going to talk about this again here in a little bit. And again, if you have any questions, feel free to send them in at any point. I'll come back and answer anything that you have. So now when we start talking about conjugates, NKA and KB, right? Because remember, like an acid is going to have a Ka value. Its conjugate base is going to have a Kb value, right? This Kw value is going to help us understand the relationship between that acid and its conjugate base, or vice versa. So just as an example, for this weak acid, hydrofluoric acid, the acid dissociation of HF, if I write out the equation, that's what it looks like, and write out the actual Ka value, it's products over reactants, everything's aqueous, so we include it. And if I write out the exact same thing for the fluoride ion acting as a conjugate base, which is going to look something like this, where it's going to be reacting with water, pulling hydrogen ions out of that solution, leaving hydroxide back as freeing up hydroxide. You don't need to be able to write what this reaction looks like. But if I write this Kb value for this fluoride, the conjugate base acting as a base, we have a Ka and a Kb value. Basically, what that Kw value tells us is that for this acid and its conjugate base, it is always going to equal 1 times 10 to the negative 14th. The reason that we know that is because this is all happening in water. It's aqueous, and the Kw of water is constant. So if you have an acid and its conjugate base, you can calculate the Kb of a conjugate base or the Ka of an acid using this relationship right here. We're going to go through an example here on the next slide. Maybe it's 2 slides away. I can't remember. But so then for a base, it's the exact same thing. If you take like, trying to think of a weak base, but basically if you take a base, figure out what the Kb of that base is, and then figure out what the Ka of its conjugate is, if you multiply those two K values together, you're always going to get 1 times 10 to the negative 14th. Again, this is temperature dependent, but again, the MCAT's not really going to make you do any calculations with that. You just need to know that increase in temperature is going to increase that Kw number. Okay. Any questions so far? This is, we're kind of stopping in the middle of a thought right here. So if you do have a question over this, I promise we're going to continue kind of exploring this on the next slide. But we can basically use this to compare how strong acids and bases and their conjugates are, right? This is like we're going to look like an actual example here, where for a given acid and its conjugate base, you multiply those two K values together, you're going to get that auto ionization constant of water, 1 times 10 to the negative 14th. So if I take a weak acid and compare it to a strong acid, HF being compared to HBr, remember, like this should be a one-directional arrow. That's my apologies. I'm going to fix that really quickly, actually. That's one of those typos that I'm not a fan of. Give me 1 second. Okay. So if we have these two acids, I need to share my screen again. What is going on here? Okay, give me 1 second. My computer is freaking out a little bit. There we go. Okay. If we are comparing a weak acid with a strong acid, like HF with HBr, the Ka of this acid, HF, is equal to 7 times 10 to the negative 4th. For HBr, it is 1 times 10 to the 9th. So obviously this number is significantly greater than the Ka for HF, right? Which means that, of course, HBr is going to be a significantly stronger acid. We'll come back to that in a second. But if we calculate its Kb using this equation, where we take that Ka, plug it into this equation, solve for Kb, we get 1.4 times 10 to the negative 11th, right? If we do the same for HBr, notice how small this number is. This is a decimal with 22 zeros and then a 1. This is a tiny number, which, remember, like we talked about earlier, this conjugate base is so weak. Where'd my pointer go? This conjugate base of a strong acid is so weak that it's not even really considered a base. It is so stable on its own that it has no interest in being a base at all, right? So whenever we start comparing these two, HBr, which we know is the stronger acid, is going to have a higher Ka, but HBr's conjugate is much weaker. HF's conjugate is a much stronger base than HBr's conjugate base, right? So basically, this sets up this relationship where the weaker the original acid or base is, the stronger its conjugate is going to be because of this relationship right here. This is the mathematical relationship that's explaining this bit of content right here. If it's a weak acid, it's going to have a relatively strong base. Not a period like strong base period. I'm just saying relatively strong, a stronger base, right? The weaker the acid, the stronger its conjugate will be. Right? Okay. We're going to keep talking about this, but through a slightly different thing. We're going to be talking about P. Again, kind of a weird thing to say, but it makes sense of why I'm just like putting the letter P up there. So anytime you take the P of something, you are taking the negative log of that thing, right? So if you're taking the P of A, you're taking the negative log of A, a log base 10. All of the logs on the MCAT are going to be base 10. Unless they're a natural log, then they're going to be base E. Like I said earlier when I first started, I have a video that's coming out to help you with logarithmic math. I actually finished it and I've already edited it. I just haven't posted it. I have no clue why, but that will be coming out. That should help with all this math that we're talking about. So just kind of applying this to that K value that we just talked about, if you plug that kind of in the same formula, if you take the pKa, that means you're taking the negative log of Ka, right? We just talked about what this Ka is, but this pKa is a new thing, right? We're creating a new relationship here. You can do the exact same thing with pKb, where if you take the P of Kb, you're taking the negative log of Kb. But logs suck, and you actually don't even need to know how to use them on the MCAT because we can actually just rearrange these equations. So I'm going to show you how to do that, right? Again, this is going to be explained in the actual video that I release. But basically, the first thing that you're going to do is you're going to move everything to one side so that the log is by itself. We're going to make the log on the right, right? So notice that all I had to do here we're just going to be working with this pKa example right here. All we had to do here was just move the negative to the other side. So then from here, you're going to make everything on this left side an exponent of 10, and then you can just cancel out the log at this point. You're basically raising everything to the power of 10. Kind of complex. You don't need to worry about how that algebra works for the MCAT. But so just to show you that, notice that now everything on the left is 10 to the power of negative pKa, which that's what that was over here. Then you just cancel out, close out the log, and you're left with Ka. From here, all you have to do is put things in a scientific notation and round. If you need to, just make sure that the percent rounding error is really small. So for example, do not round 1 to 2, but it's totally okay to round like 8.9 to 9, 8.5 to 9. Even that's fine. Basically, just as long as you're not changing the number by a large percentage, any rounding is fine. Rough math on the MCAT is going to be more than good enough. So for example, like if this is your Ka value that they give you, just go ahead and throw that into scientific notation. So then basically from here, this gets really easy because these exponents are essentially equal to each other, right? So basically, whenever I write this out, notice that this negative pKa is basically going to be equal to negative 5. So because of that, pKa is equal to 5. So whenever you're writing this rearrangement like this, all you really have to do is look at the exponent of the scientific notation of this Ka value, and that's going to tell you what this pKa is. Like I can look at this number right here. If this is my Ka value, I can immediately tell you the pKa is 5. That's all you have to do, right? This is significantly easier than trying to remember all of the log rules. Like a log of 0.1 is something I to this day have no clue how to solve logs. But if you use this rearrangement, it's going to be significantly easier, right? To where all you have to do is look at the exponent of the Ka value in scientific notation. And that's pretty much going to be what your pKa value is. You can do the same thing with pKb and Kb, right? So just like as another example, let's just say that your Ka value is 5 times 10 to the negative 5th. Like slightly more complex because now this number right here isn't 1, it's 5. Again, your pKa is basically going to be equal to 5, right? So that's where we're going to start off. We're going to start off with a pKa of 5. But since this number right here is greater than 1, just decrease it a little bit. You can estimate. Don't have to, it doesn't have to be a perfect number, but just decrease it slightly, right? So like I'm just estimated here, the pKa is going to be equal to 4.6-ish, right? That's close enough. That math on the MCAT is more than good enough because basically it's a multiple choice exam. You're going to have answer choices that are significantly different from each other, like 1, 4.6, 5.9, and 12. So if you can make rough estimations like this, where you do this rearrangement, figure out what the pKa is just based on that exponent, and then make a little bit of an estimation like we did here, you're going to be perfectly fine, right? Again, we're going to revisit this. We're going to be doing a little bit of practice of this. We're going to revisit a few times. But does anyone have any questions about how to start simplifying some of this math that we're going to be doing? And we're going to talk about what this pKa value actually is. It's like we talked about how to calculate it, but why did we calculate this? We're going to talk about that here in a second. So let's talk about what this thing actually is. We just talked about how to calculate it using that little rearrangement thing, but let's talk about what it actually is, right? So while you should still have these equations memorized because maybe they're just going to ask you to regurgitate it on the exam, it's going to be much easier to actually do math with these rearranged forms. So like I said, all you have to do is put this Ka value into scientific notation, and the exponent of that scientific notation is basically going to be equal to your pKa. That's it. And then, like I said, if the coefficient of the scientific notation is greater than 1, you can just decrease it a little bit, like estimate like by like 0.1 or 0.2 or something like that. Doesn't matter. It's going to be a good enough estimation. Same thing with KB and PKB, right? Not necessarily. Sometimes they'll give you a Ka value that's like 0.001 or something like that. So it's like, I'm just saying, like, yeah, so 0.001 is not in scientific notation. It's a little bit harder to equate 10 to the power of negative pKa equal to 0.001. So it's just easier to put it into scientific notation because that's 1 times 10 to the negative third. So because of that, then the pKa is equal to 3 because the exponent is negative 3. So that means my pKa is equal to negative 3. So not always. It usually will be, but it doesn't always have to be. That's why I added that step, just to make sure that you do put it in a scientific notation. So like I said, like why do we need to know what this stupid ass pKa or PKB thing is, right? So basically it's just a scale to make it easier to understand what's going on with Ka and Kb, right? Because like if you notice a lot of those Ka values, it's like 1 times 10 to the negative 7th. That's not a very intuitive number, right? This is basically going to put it on that scale of 0 to 14 that you're probably already familiar with pH. But it's basically doing that exact same thing. It's basically taking the exact same information, but just putting it on a scale that makes sense to us, right? So when we have this pKa scale, specifically for pKa, the closer to 0 the pKa is, that means it's a stronger acid. Or the closer to 14 it is, the weaker the acid is. So if it's a pKa of 1, that's a really strong acid. If it's a pKa closer to like 13 or 14, that's a super weak acid. In fact, it's so weak that it's actually going to be a base. So, and again, of course, we can do the exact same thing for pKb, right? Where the lower the pKb value is, the stronger base it is. Everything we're talking about for acids with pKa, Ka, hydrogen concentration, all that sort of stuff, we can invert for pKb as well, bases. Right. And this is going to lead into some important discussions later when we're talking about what's happening with acids based on the pH of a solution. Right. If you've ever seen like the isoelectric focusing, that's like the idea of like, how can I figure out what the charge of this amino acid is? This is what this is going to be helpful for, right? That's what we're leading into. So now to actually build that relationship between those two things, right? Like what happens to pK if we increase Ka, right? We're going to use 2 examples. So acetic acid, just a reminder of what that rearranged equation is, where if we put the Ka in scientific notation, the exponent's basically going to be equal to the pK, right? So notice that the Ka for acetic acid, this exponent is negative 5. So my pKa is going to be roughly 5, essentially. And notice that I just decreased it a little bit because this number is greater than 1. If we do the same thing for sulfurous acid, which is a weak acid, not sulfuric acid, this is sulfurous acid. It's a different thing. Again, really annoying with the naming conventions of Gen Chem, but I don't make the rules. Sorry. Notice that this Ka value is larger. It's kind of confusing because these are negative exponents, but it's larger, right? It's closer to the smaller a negative exponent is, the larger the number is, because that means there's less zeros in between the decimals. But so this pKa is going to be right below 2. So I just estimated it to be 1.9-ish. Right, so now when we actually start comparing these two things, notice that acetic acid has a greater pKa, but it has a lower Ka. That's an inverse relationship. So if you increase the Ka, that leads to a decrease in pKa. So what does that mean about a decrease in pKa? If I decrease the pKa, is that a stronger acid or a weaker acid? Stronger, right? We already know that an increase in Ka or a decrease in pKa leads to a stronger acid, right? The higher the Ka value is, the lower the pKa value is, the stronger the acid is, if that makes sense. All of these are saying the exact same thing. It's just we have this weird inverse relationship here. So conversely, if you have a lower Ka value, that means it's going to have a higher pKa value and therefore be a weaker acid. Right? Basically, the relationship between Ka and pKa is inverse. The higher the K value is, the lower the pK value is. Right? So the same logic is going to apply to pKb. Right? Increasing the Kb value leads to a decreasing pKb, which is a stronger base. Right? Same thing, inversely proportional. Higher Kb, lower pKb, stronger base. Lower Kb, higher pKb, weaker base. Right? That's the relationship between Kb and pKb, right? It's the same information, it's just on a different scale for it to make more sense for us intuitively with 0 to 14 rather than magnitudes of decimals. Okay, so we're going to keep applying this information to all of that stuff that we've talked about earlier with what acids are and conjugate bases and stuff like that, right? So again, we already know that weaker acids have stronger conjugate bases, right? The weaker the acid, the stronger the conjugate base, and vice versa, of course, for bases. So that same relationship that we just looked at that last slide, the higher the Ka, the lower the pKa, the stronger acid, it's going to have a weaker conjugate base. So you can predict that if an acid has a high Ka, it's going to have a weak conjugate base, a weak Kb, right? Same relationship for the bases as well. We're not going to go through all of that right now. So because we've already established that the Ka and a Kb for a specific acid and conjugate base must multiply to this number right here. The pKa and the pKb of that same acid and conjugate base pairing are going to have to add to 14. Right? I know that seems like randomly out of the blue, like where did that number come from? But like let's prove it really quickly, right? So let's look at hydrofluoric acid. So hydrofluoric acid is a weak acid. It's not going to dissociate fully. It's going to have a relatively high Ka value, right? So whenever we write the dissociation of hydrofluoric acid, this is what it looks like. Where if we write that rearranged stuff that we talked about earlier, if we start over with the Ka of hydrofluoric acid going in this direction to the right, it is equal, the Ka value is equal to 7 times 10 to the negative fourth. If we calculate that pKa, it's going to be right around 4, which, like I said, since this number is greater than 1, you just decrease this number a little bit. pKa is 3.3-ish. That's close enough, right? Close enough math for the MCAT, right? But we can also calculate the Kb of this conjugate base right here, the fluoride ion, right? Where the Kb of the fluoride ion, we can just plug it into that equation right here to solve for the Kb. We don't have to go through and do the whole product of a reaction thing. We could if we wanted to, but we get the same answer. Where whenever we solve for the Kb, we get 3 times 10 to the negative 14th. And so your pKb is going to be equal to this exponent essentially. And then you just decrease it because this number is slightly greater than 1. So it's going to be right around 11, just slightly lower. So that's why I estimated to be like 10.7-ish, right? So we already know how to do that. That's something that we covered a few slides ago. Ka times Kb is equal to Kw. This is nothing new. But whenever we calculate the pKa and the pKb from those numbers, if you add them together, 3.3 plus 10.7, we get 14. So just like this Kw must always be equal to 1 times 10 to the negative 14th, basically the pKw is always going to be equal to 14. So because of that, pKa plus pKb, this equation right here, is always going to equal 14. Right? Any questions about that so far? And again, I know this is like we're kind of explaining a lot of math right now, and we're going to start explaining over the next few subjects of why this is all important. I'm just showing you how to calculate this stuff and what it means. Like, so for example, I'm hoping that you know right now, what does it mean if something has a high Ka? If it has a high Ka, low pKa, strong acid, stronger acid, which also means that everything about that conjugate base is going to be the opposite. Right? Okay. So now again, we need to make that disclaimer about temperature, right? So like we talked about earlier, increased temperature is going to increase that Kw value because it's increasing how much of that water dissociation happens, how much of that water auto ionization happens. And we also know that any change we make to K is going to be an inverse change to the pK value, right? We already talked about that, where a higher Ka means a lower pKa, right? So they're inversely proportional. So while pKa plus pKb must always equal 14 at 25 degrees Celsius, which, like I've been saying, you can just assume it's at 25 degrees Celsius unless you're told otherwise. And remember, we don't really care about Celsius on the MCAT. You want to convert this to Kelvin. Um, uh, Basically, since we know that an increase in temperature will cause an increase in Kw, that means it's going to cause a decrease in pKw, and therefore this number is going to be less than 14. So if you get a question that's basically saying that like we added the pKa and pKb and they ended up being 13, what did we do? That means we increased the temperature, right? If this pKw value, this 14 number decreases, that means you increase the temperature. Conversely, if you decrease the temperature, that leads to a decrease in Kw. There's less water auto ionization happening, less product forming, which corresponds with an increase in pKw, the negative log of Kw, which means that this is actually going to be greater than 14. So likewise, if they say that we added the pKa and pKb of this acid and we got 17, what happened? You decrease the temperature. Right? That's basically what this slide is trying to get at. These two relationships right here are basically what I recommend knowing for the MCAT. Realistically, you don't need to necessarily understand why. This is one of those things that if you just know what's going on, you're going to be fine. Right? Okay. So from here, this is where we're going to start talking about polyprotic acids and pKa values and that sort of stuff. So remember, as Ka and Kb get higher, pKa and pKb respectively are going to get smaller, right? Inverse relationship. Hopefully that's been hammered in now at this point. They're inversely proportional because we use them to calculate each other and it's an inverse scale. So both of these things, having a low pKa and low pKb, or having a high Ka and Kb, both of those mean that the species that we're talking about is getting stronger, right? So for example, polyprotic acids, this is something that I was kind of alluding to earlier, they're going to have multiple pKas because they have multiple hydrogens to be donating. But those pKa values are going to get progressively weaker. So for example, let's look at the dissociation of H3PO4. The first acid dissociation of H3PO4 gives us a pKa of 2, right? That's what I'm giving you. You don't have to calculate that, right? This would be a Ka value of 1 times 10 to the negative second. If you can do that swap hopefully pretty quickly now because you know that this is just equal to the exponent of the Ka value. But if we keep going, because notice that this conjugate base right here is technically amphoteric, it can actually donate a proton as well. It can theoretically go backwards because this is a weak acid acting as a conjugate base, but it can still act as an acid as well. So let's look at what happens when it does act as an acid. Whenever it donates another hydrogen to become HPO42 minus, notice the pKa went up. It's getting weaker. It's pretty significantly weaker, right? This is not a very strong acid at all. So basically, as this polyprotic acid keeps donating hydrogens and starts evolving to different protonation states, it's going to start getting weaker and weaker as we keep going, right? Like the desire for this thing to basically act as an acid is getting worse over time. And we'll talk about how we can actually still convince it to act as an acid in a little bit. whenever we compare pKa to pH values. We'll talk about that later. I know someone had a question about that earlier. And we can even do this one more time. There's still another hydrogen that we can donate here, and that's what's being shown in this reaction right here, where this reaction has a pKa value of 12, which means that this is so weak of an acid that it's not even really going to act as an acid, if that makes sense. And in fact, the reverse reaction is more likely to happen, essentially, at this point. So because many of these conjugates are amphoteric, meaning that they can kind of go both directions, right? Just like the weak acids of like weak acids and their conjugate bases. What am I trying to say? Like this is the best example right here. This H2PO4, it can potentially go in the reverse direction and act as a base, but it's a very weak base whenever it does that. Its pKb value would be 12 because pKa plus pKb must equal 14. So this H2PO4 can go backwards or it can go forwards and act as an acid, right? So let's do that really quickly. Let's compare Ka to Kb of like the conjugates. So whenever H2PO4 acts as an acid in this reaction right here, it has a Ka value of 6 times 10 to the negative 8th. Again, I've estimated that up here to be 7, right? I do some rounding errors whenever I'm making these slides. Whenever it acts as a base, meaning it's going in the reverse direction of this initial reaction, it has a Kb value of 1 times 10 to the negative 12th. So whenever this thing acts as an acid, its Ka value is 6 times 10 to the negative 8th. Whenever it's choosing to act as a base, because it's amphoteric, its Kb value is 1 times 10 to the negative 12th. So basically, this is just where I'll ask you the question, which one do you think H2PO4 is more likely to act as? Is this more likely to act as an acid because of this Ka value, or is it more likely to act as a base because of this Kb value? Which one do you think it's more likely to do? Which one is it better at based on these two values right here? It's more likely to act as an acid, right? So because of that, that's one of those things the MCAT might ask you to do is figure out, okay, with this species right here, is it more likely to act as an acid or a base? And you can predict that based on that thing's Ka or Kb values. If it has a higher Ka value, then it's going to be acting as an acid. It's more likely to donate this hydrogen. If it has a higher Kb value, then it's going to be more likely to act as a base, right? So like, for example, HPO4 2 minus, its pKb value is higher than its pKa value. So it's more likely to act as a base than it is an acid. Right. So one thing I will clarify is these two numbers, we cannot use these two numbers together because we're talking about the same molecule. We use that Ka times Kb is equal to 1 times 10 to the negative 14th for an acid and its conjugate base, if that makes sense. Like H2PO4 and HPO4 2 minus. We can take the Ka of H2PO4 and the Kb of HPO4 2 minus, and those are the two numbers that we know are always going to be equal to 1 times 10 to the negative 14th. Here in this example, we're literally talking about H2PO4 in two different scenarios. Acting as a base, which is in this forward direction, acid, which is in this forward direction, or acting as a base, which is in the reverse direction up here. Two different reactions. So there's going to be two different Ka and Kb values. Yeah, you really good clarification to ask. Thank you. But so basically, for a given molecule, we can predict if it's going amphoteric molecules, which often the conjugates of polyprotics often are. The conjugates meaning like these the conjugate bases of this initial acid. The higher the Ka value is, the more likely it is to act as an acid. The higher the Kb is, the more likely it's to act as a base. We can compare them to each other, but we're going to be getting those values from different equations, essentially. Okay. So this is a good time for us to take another quick little 5-minute break because we're going to start combining pretty much everything that we've talked about so far. We're going to be combining acids, bases, pKa, pKb, Ka, Kw, whenever we start talking about pH, right? Where this is going to be kind of the section where everything starts coming together now at this point, right? So we'll take a 5-minute break and we'll come back at 15 after 9:15 Eastern, if that helps. But yeah, I'll see you guys back here in a few minutes. All right, welcome on back. We'll probably, it depends on the time. Like I'm obviously maybe you're not back yet, but I'm going to start lecturing again here in a second. Depending on how much time we have left, whenever we get to kind of like my next scheduled break, we might take a longer one just because I know it's been a long time. And like I said, I want to make sure that you guys are kind of rested and not overwhelmed. But even if you are, you have the notes in front of you, you're getting the recording, you can go back and watch anything that's confusing. Right. So just to kind of keep moving forward, like I said, so basically what we've done so far is we've defined the types of acids and bases, what that means, how to predict what makes a good acid versus a bad acid, and what that means as far as like salt, the common ion effect, that sort of stuff. We talked about Ka, pKa, and that sort of stuff. But basically, that whole section on Ka and pKa, that's basically describing the strength of an acid, right? This is how good an acid is at donating its proton, right? Where basically it's the same information, just regurgitated in a different way. The Ka is the exact same thing as the pKa, just kind of it's on a different scale, essentially. This is the section that we're going to talk about what that actually means. What does a pKa value actually mean? What does it tell us, essentially, right? So in order to do that, we're going to be bringing pH into the equation now. I think all of you probably have somewhat of a good understanding of what pH is, but this is what we're going to fully dive into now. So basically, the pH is the measure of how acidic a solution is due to the hydrogen ion concentration, right? Notice that this is the acidity of a solution, not the acidity of an acid, right? This is talking about everything that's going on at the same time. Acid is literally just saying like, okay, this is how acidic this acid is. pH and pH and pOH are telling us how strong the solution is as an acid or the solution is as a basic. It's going to be the same thing as Ka and Kb, that basically all of the logic that we apply to pH, we're going to be able to apply to pOH as well, just for bases instead of acids. Right. So again, just to clarify, pKa and pKb measure the strength of an individual acid or base. It is simply saying like, this is how strong this acid is. pH and pOH are telling us how strong the solution is, if that makes sense. That's the difference between the two. So remember, like we said earlier, anytime you take the P of something, again, weird comment, but anytime you take the P of something, you're taking the negative log of that thing, right? So anytime we take the pH, we are taking the negative log of H, the negative log of the hydrogen concentration, which we can rearrange in the exact same way. We move this negative to the other side, raise this side to the power of 10, and we get 10 to the negative pH is equal to the hydrogen concentration. This is the equation I recommend using. This one, unless you have your logs memorized, is not really going to help you very much. This one over here is really easy because like we talked about with Ka, all you have to do is just look at the exponent of this number, and that's going to equal the pH. That's pretty much it. Maybe make a little estimation after that, right? Where basically this sets up the relationship where the higher your hydrogen concentration is, the lower your pH is. And this corresponds with the solution being more acidic and less basic, right? Like the higher number of hydrogens there are, that's a more acidic solution. Where for pOH, it's the exact same information, just like I said, through the lens of bases rather than acids. If we take the pOH, that is the negative log of hydroxide. That whenever we rearrange that, we get 10 to the power of negative pOH is equal to the hydroxide concentration. So if they give you a hydroxide concentration, put it in scientific notation, look at the exponent. That exponent is going to tell you the pOH. That's all you have to do. Maybe make a little estimation after that if the coefficient's greater than 1, but that's it. Right? Where this sets up that relationship where similarly to pH and hydrogen concentration, the higher the OH, the lower the hydroxide concentration, and this is a more basic or less acidic solution, right? These are very important relationships that you need to have memorized, that like they're pretty intuitive, and they're not super intuitive because logs are not very intuitive, but basically these are kind of simple relationships that the MCAT, it's going to make your life way easier to understand what's going on the MCAT if you understand these basic relationships. I'll explain why whenever we get to our first practice problem here in a little bit. So just to show you an example of how easy this is, right? So if we are asked to calculate the pH of a solution that is, it's a 10 milliliter solution containing 0.00001 moles of HBr, right? Remember that like in order to calculate pH, we need to get the hydrogen concentration. So we're going to have to do some work here. But one thing that I want to explain really quickly, what type of acid is HBr? Is this a strong or a weak acid? Strong, right? So it's going to dissociate fully, meaning that all of this HBr is going to turn into hydrogen ions and bromide ions, right? We're going to draw this out in a little bit. One thing I want to clarify really quickly is that whenever you get this concentration of HBr, it's actually going to be exactly equal to the hydrogen concentration because of that fact. However much hydrogen bromide, not hydrogen bromide, hydrobromic acid you have, whatever that concentration is, all of it's going to be turned into hydrogen ions and bromide ions. So basically, what I'm trying to say is the concentration is equal. But just to kind of show you what I mean by that, like if you just have 10 molecules of A bound to B, if you break those up, you still have 10 molecules of A and 10 of B. It's not like you get 5 of A and 5 of B. You still have 10 of each, if that makes sense. So likewise, whenever we're figuring out the hydrogen ion concentration, all we have to do for these strong acids and bases is figure out what this acid concentration is. And that acid concentration is going to equal the hydrogen concentration. Right? Same thing for bases and hydroxide concentration. We're actually going to do this math here in a second to prove it. But one thing I will point out is like things get a little bit weird whenever you get like a polyvalent polyprotic acid or base. We'll talk about that in the next question. But so in order to actually do this math, you're going to get an exposure to my chicken scratch handwriting here. So sorry about that. But so in order to actually write out what's going on here, we have HBr, which is dissociating into a hydrogen ion and a bromide ion, right? All of these things are aqueous. So basically, whatever this concentration of HBr I get, that concentration of HBr is going to be equal to my hydrogen concentration, because for every 1 mole of HBr, we make 1 mole of hydrogen. But we need to calculate that hydrogen. We need to calculate that concentration first, right? So we have 10 milliliters and 0.001 moles of HBr. So we need to convert this to concentration. So concentration is equal to moles per liter, which in this example, I'm going to immediately convert this stuff into scientific notation. 0.0001 moles is equal to 1 times 10 to the negative fourth moles. And this is over the liters, which 10 milliliters is the same thing as 10 times 10 to the negative third liters. It's the same thing. It doesn't really matter how you do that. We are going to do some simplification here. In fact, I'll go ahead and do that right now. 1 times 10 to the negative fourth moles over 1 times 10 to the negative second liters. That's the same thing as 10 milliliters. Like again, I know that this math is not the easiest thing to kind of do, especially if this is your first exposure to scientific notation math. But like I mentioned twice so far in this lecture, I do have a video that's coming out to make this a lot more simple, right? We're going to do it right now here together, but I'm just letting you know that there's another video coming. So basically from here, all we have to do is just basically simplify this expression where we're going to kind of split this up, and 1 divided by 1 is equal to 1. And 10 to the negative fourth power divided by 10 to the negative second power, all we have to do here is we have to subtract the exponents. -4 minus -2, which that's going to give us 1 times 10 to the negative second molar. That's our concentration, right? Let me just check that math, because I might have done my math a little bit wrong in one of these answer choices. That's okay. We'll look at this here in a second. I think I did my math wrong when I actually made the answer choices, but on the MCAT, your job is to pick the closest answer to what you have. So just bear with me for a second here. Sorry about that. So, and it's possible that I did the math wrong somewhere in the middle here. It doesn't look like I did, but my apologies if I messed something up. Sorry about that. But so basically what I'm trying to say is this is the hydrogen concentration, right? They didn't give it to you. You have to calculate it. This hydrogen concentration is the exact same number because of what we talked about right here. Right? So because of this, I can just plug this number straight into the pH equation, where 10 to the negative pH is equal to the hydrogen concentration, which is equal to 1 times 10 to the negative second. And so therefore, my pH is going to be equal to 2. Right? I don't know what went wrong here whenever I was actually creating this question. But long story short, we're just going to go with C because that's the closest answer that we have. Right? I might have done like my 10s wrong or something like that, but that's my bad. But long story short, as soon as you have the concentration of a strong acid, all of that's going to be equal to the concentration of hydrogen ions. All you have to do is plug it into the equation. Right? Just as another example, let's do it with a base. Right? Calculate the pH of a solution that contains 0.005 molar calcium hydroxide. So likewise, we're going to write out the whole reaction. Everything's aqueous. This is a strong base. So we're going to get calcium 2 plus and 2 of these hydroxide ions. So my concentration of calcium is 0.005. But so what do you think my concentration of hydroxide is going to be? If every one molecule of calcium hydroxide makes 2 molecules of hydroxide, what do I have to do to this concentration in order to accurately represent the hydroxide concentration? Do I leave it the same, or do I have to double it, or do I have to half it? Right, we have to double it, right? Because this is telling you that for every 1 mole of calcium hydroxide you make 2 moles of hydroxide. So my hydroxide concentration is going to be 0.00, 0.010 technically if we're doing sig figs, but sig figs don't matter for the MCAT. So from here, we can just regurgitate this straight into the POH equation. 10 to the negative POH, because that's what we're looking for, that's our goal, is equal to this number written in scientific notation. That hydroxide concentration, written in scientific notation, which is 1 times 10 to the negative second. I'm going to write up here, my bad on the math. Sorry about that. So because of this, our POH is going to be equal to 2. Right? So the answer here is going to be A. Right? Any questions about how we calculated any of that? Any questions about strong acids and bases? The math is super simple. Just figure out what the concentration of the strong acid or base is. That's going to be equal to the hydroxide or hydrogen concentration. Just plug it straight into that equation that we've been working through. Right? And like I said, I messed up this math. That's my bad. I messed up the answer choices when going through one. Sorry about that. That's my bad. I'll go back afterwards and check to see where I made that mistake, and then I'll correct it and send an email about it. Maybe we'll see. Yep, sorry, I'm imperfect. My bad. This is my first time going through this, so that's my bad. Not catching my math errors. Okay, so that's how you can calculate the pH or POH for strong acids and bases, right? It's really simple, really easy to do, really easy stuff for strong acids and bases. You just got to calculate the concentration of that strong acid or base, plug it into that equation. That's pretty much it. So just to kind of expand on this a little bit, because the Kw of water is equal to 1 times 10 to the negative 14th, which corresponds with a hydrogen and hydroxide concentration of 1 times 10 to the negative 7th, we can take the pH and POH of these two numbers. Just like earlier when we took the Ka and the Kb and we turned them into pKa and pKb. We can do the same thing here. And what we end up with is a hydrogen concentration of 1 times 10 to the negative 7th is equal to a pH of 7. A hydroxide concentration of 1 times 10 to the negative 7th is equal to 7. Right? So basically, this is telling us that because the Kw of water is always 1 times 10 to the negative 14th, the pKw, which is going to be the sum of the POH and pH, is always going to be equal to 14. Right? In pure water, the pH is 7, the POH is 7. Right? And so because of this, through the same relationship that we saw with pKa and pKb that they add to get 14, same thing happens here. the pH plus the pOH must equal 14 for a given solution. This is talking about for a given acid or base and its conjugate. This is talking about the entire solution as a whole, right? And again, this is at 25 degrees Celsius. We'll talk about how that changes with temperature, of course, as you can expect. So the important relationship that this sets up is that in order to increase acidity, you can actually do that in two different ways. Of course, you can increase the hydrogen ion concentration, which is going to decrease pH. But you can also decrease hydroxide concentration, which increases pOH. You can do either one, right? Remember earlier we had some salts that what they were doing is they were removing hydroxide from solution, which made it acidic. Right? It's the same thing here. This is mathematically proving that in order to make this number go down, I can either increase this hydrogen concentration or I can decrease hydroxide concentration to make pOH larger. You can do either one, right? So same thing for basicity. Yeah, pKa is the molecule, pH is the solution, right? And we're getting really close to relating the two with each other here in a second. So it's the same exact thing for basicity. You can increase basicity in two ways. You can decrease the hydrogen concentration, which is an increase in pH, or the one that you're probably expecting is an increase in hydroxide concentration corresponds with a decrease in pOH. Either one's fine. Either one works, doesn't matter, right? Okay. With that being said, like I said, we're going to go through and talk about how to calculate pH and pOH of weak acids and bases, and then we're going to start relating pKa to pH, right? So while calculating the pH of strong acids and bases was super easy and simple, it is not that simple for anything that's weak, right? Because they don't fully dissociate. So like, for example, if we take HF, which is a weak acid, we can't just assume that the hydrogen concentration is equal to the HF concentration because not all of this HF is going to dissociate into hydrogen ions. We could do that with strong acids and bases because they fully dissociate. We can't do that here, right? So it's not as simple as just plugging in the concentrations into that equation that we already saw, right? So what are we going to do instead? The first thing that we're going to talk about is what are called ICE tables, initial change equilibrium tables. Right? This is specifically what you're going to be using when they only gave you one concentration, like the concentration of a weak acid or a base, not both. And that will make sense whenever we get to the other example. Right? So basically, for example, we're calculating the pH of a solution if this is the concentration of HF given this Ka. Right? So let's just write out what this dissociation looks like. It's bidirectional because it's a weak acid. So we're going to get a little bit of HF in the solution. It's not fully going to be turned into hydrogen ions. So the goal is to figure out what this number is, what this hydrogen concentration is. Once we have that hydrogen concentration, we can plug it into our pH equation, right? So what we're going to do is we're going to set up what's called that ICE table, right? I do not remember putting that animation on that. Sorry. That completely threw me off guard. I was not expecting it to be like a cheesy little rotate thing. Sorry. So basically, the first thing that we're going to talk about is the initial setup, right? Initially, the only thing we've put into the beaker is this amount of HF, that concentration of HF. There's no hydrogen ions. There's no fluoride ions, right? We haven't added any hydrogen or fluoride ions, right? The change is simply how much we're expecting the concentration to change. That's what we're solving for. We're solving for X. We're trying to see how much this concentration is going to increase because that's going to tell us our hydrogen concentration. So because HF is dissociating, we're going to have a subtraction of X to get the final concentration of HF. And for these two, we're going to be adding X, if that makes sense. Because basically, let's just say like 20% of this hydrogen concentration dissociates. That means we're going to lose 20% from this number, and we're going to gain 20% in both of these. I mean, you can't gain 20% of zero, but basically what I'm saying is both of these numbers are going to increase by that same number essentially, right? So basically we are adding these two numbers together to get to that equilibrium concentration. So once we're at that equilibrium concentration, we just plug in these numbers down here like this, right? You just add these two together and you end up with a setup like this, where we know that at equilibrium, the concentration of HF is going to be whatever this concentration is minus however much HF dissociates. And that is going to dissociate into hydrogen ions and fluoride ions, right? It's basically what this is telling us. Now that we have an expression for these equilibrium concentrations, we can plug those into our equilibrium constant, right? The equilibrium constant is like Ka, right? This is an acid dissociating. Ka is a measure of how strong an acid is at dissociating. So just to show you that, Ka is equal to the equilibrium hydrogen concentration times the equilibrium fluoride ion concentration divided by the reactant here, which is that HF. Everything here is aqueous. If it doesn't have a state on it, it's aqueous. And then we can just plug in these numbers, right? So 0 plus X, that's just X. So my hydrogen ion concentration is X. My fluoride ion concentration is X. And notice right here that for the HF concentration, I just ignored X. This is basically something that you're going to be able to do anytime you make these tables on the MCAT. You're always going to be able to just ignore this X in the denominator. The reason for that is these acids are so weak that basically the amount of dissociation happens here is negligible compared to how much concentration this is. That's basically why you can just ignore it on the bottom, if that makes sense. You can't ignore it on the top because we literally had nothing. So even if you're only getting a tiny bit of product, it's enough for us to include it. But we're not losing a bunch in the denominator, so it's not going to make a rounding error. So basically, long story short, for the reactant, you can just ignore the minus X. Right? There technically is a situation that you're supposed to include it. It depends on what this number is, but on the MCAT, you're never going to see that. I would bet my cat on that, wherever he is right now. Realistically, I wouldn't bet my cat on that because, again, like I talked about earlier, disclaimer, I don't know what's going to show up on the MCAT, but in my years of studying and teaching and tutoring for this exam, I have never seen them make you include this number here. So you just ignore that. That's why I've dropped it. And they gave us what this Ka is equal to. It's equal to 7 times 10 to the negative fourth. So I can start solving for what my X is, which is going to be equal to what my hydrogen concentration is right here. Right, so this is where I stopped. I stopped by turning this into scientific notation and multiplying it over. And again, this is where I'm going to pick up with my chicken scratch handwriting, right? Where basically, there it is, sorry. Basically, X squared is going to be equal to 1 times 7, which is just going to be 7. And then 10 to the negative fourth times 10 to the negative fourth. And so what you're just going to do here is you're just going to multiply, you're going to add the exponents together. So 7 times 10 to the negative fourth plus negative 4 is negative 8. That is what my X squared is equal to. We're going to take the square root of both sides, where basically X is equal to the square root of 7 times the square root of 10 to the negative 8th power. We can simplify this. I'm going to estimate the square root of 7 to be somewhere around like 2.5. That's close enough for me. If it's close enough for you, it's somewhere between 2 and 3. 2 squared is 4, 3 squared is 9, so it's somewhere in the middle. I'm just going to say 2.5. As my dad used to say, close enough for jazz or close enough for government work, whatever you want to say. This is a multiple choice exam, so all of these estimations are going to be more than good enough. And then all we have to do with the scientific notation stuff is if this is a square root, we just divide negative 8 by 2. So times 10 to the negative fourth. This is my X, which is equal to my hydrogen concentration. So I just used my Ka value over here, and I used this ICE table to figure out what X is equal to, which is going to tell me what the hydrogen concentration is. Right? So now that we have this hydrogen concentration, we can drag it up here. And since the hydrogen concentration is equal to 10 to the power of the negative pH, 2.5 times 10 to the negative fourth is equal to 10 to the power of negative pH. Remember, basically, this exponent right here is going to be right around where your pH is. So I'm going to estimate that the pH is kind of around 4, but since this number is greater than 1, I'm going to decrease 4 a little bit and just say pH is equal to roughly 3.7. That's good enough. Your answer choices would be like 1, 3.7, 4.9, and 14, right? So it's going to be pretty easy to make little estimations like this and still get at the right answer, right? So that is the pH. So remember, we had to use this ice table when it was a weak acid, and they only gave us the concentration of that weak acid, right? That's the only thing that they've given you. That's the condition for when you're going to be using these ice tables, right? Any questions about using ice tables so far before we jump into the next thing? Because the next thing that we can do is use the Henderson-Hasselbalch equation. Because this is actually going to be even easier than ice tables, but this is whenever they give us an acid and a base. This is when instead of just giving us the concentration of one thing, they're giving us the concentration of both an acid and a base. This anytime you're doing any sort of neutralization where there's an acid and a base put together in some way, even if it's not a full neutralization or anything like that, you're going to be using this Henderson-Hasselbalch equation, right? Like buffer systems. Buffer systems is a acid and its conjugate base. We're going to talk about those in a bit. We're going to be able to use this HH equation, the Henderson-Hasselbalch equation. So basically, this ends up being really easy. We can just use this equation where for acids, the pH is equal to the pKa plus the log of the concentration of the conjugate base divided by the concentration of the acid, right? Again, but here's another really ugly log. We're going to get rid of this here in a second. We're going to create a shortcut. So we can do the same thing with POH where just notice everything changes. The conjugate base is turned into a conjugate acid. Instead of pKa, we have pKb, right? Straightforward as usual. But since logs suck, we can simplify this pretty easily, right? So for acids, in order to simplify this for an acid, there's basically three steps that we're going to do. We are going to make sure that we have the pKa, because maybe instead of giving you the pKa, they give you the Ka, right? Kind of annoying, but they're going to do that. Anytime you have the Ka, you can immediately turn it into the pKa and vice versa. Should be pretty easy to do. Once you have that pKa, the next thing that you're going to do is just look at the concentrations that they gave you. Is there more acid or is there more conjugate base if we're talking through an acid example? From there, if there's more acid, then the pH is just going to be slightly more acidic than the pKa. If there's more base, then it's going to be slightly more basic than the pKa if there's more base than there is acid. Right? And then for bases, everything's the same. You're just swapping all of these terms out with the basic ones, pKb, kb, POH, right? So with all of this being said, like I said, we're going to use we're going to basically use this for an actual example here, just so you can actually see this, right? Gosh. So with an actual example, let's calculate the pH of a solution that contains 1 times 10 to the negative fourth of this ammonium hydroxide. In addition to that, notice that they've also given me the concentration of the conjugate acid. Right, so this is some semblance of like a neutralization reaction or like a buffer solution, something along those lines. Basically, we just have an acid and a base. Doesn't matter if it's a neutralization or buffer reaction. Anytime you have both an acid and its conjugate base, we're using the Henderson-Hasselbalch. So this is a weak base. And notice that we're trying to solve for pH. So that's the first thing that I recommend doing is anytime you get a math question, making sure you know which one they're giving you and which one they're looking for. We're going to have to calculate pH and convert it to pH at the end, but that's easy. It's just pH plus POH is equal to 14. Really easy to do, but just keep that in mind. We are going to have to do that, right? Definitely one of the first steps that I recommend always being sure of. So given that the Kb is equal to 2 times 10 to the negative fifth, we can solve for the pH of the solution. That we have all the information that we need because we can plug it all into this Henderson-Hasselbalch equation, right? Well, you'll notice I'm not even going to be plugging into the numbers into the equation. We're just going to estimate it really quickly. So the first thing that we need to do, so Kb, because this is a base, since the Kb is describing how strong the base is, right? Given that this ammonium molecule right here, this weak base, it has a Kb of 2 times 10 to the negative fifth. Oh, I just told you it. I was given. Yeah, sorry. That's why I put it in parentheses. I didn't. Yeah, sorry about that. You're not supposed to like be able to calculate it or anything based on what I've told you so far. This is given. That's my apologies. I'll write that in. Yes, it was given. Thank you for that. So from here, the first step is we need to make sure that we calculate the pKa. right? Because the KB is not really going to help us for this equation. So 10 to the power of negative PKB is equal to the KB. So basically this exponent is going to be equal to your PKB. And then just drop it a little bit because this is a 2 out in front. So that's where I got that this PKB is somewhere around like 4.8. It's a close enough estimation for the MCAT, right? We have the PKB, so that's our starting point. From here, is there more base or is there more conjugate acid? Which one do I have a higher concentration of? This initial base or the conjugate acid? Which one? A higher concentration of the base, right? So because of that, in step 2, that just means that it's going to be, we have a higher concentration of base than the conjugate acid. So because of that, the POH is going to be slightly lower, slightly more basic than the pKa, right? So just drop it a little bit. It's going to be a little bit more basic than whatever the pKb was. I'm sorry if I've been accidentally saying pKa. My brain's on acid mode right now. Kind of sound like I said I'm on acid. Sorry. Weird way for me to word that. But basically, since we're talking about bases, pKb and POH, if basically if there's more base and we're talking about POH, adding more base is going to drop that POH, which is why I've estimated this just to be around like 4.5. It doesn't matter as long as you know that the pH is just going to be slightly lower than whatever the pKb was, right? But again, this is POH. That's not what we're looking for. We're looking for POH, so we just have to plug it into that equation to get 9.5, right? Which makes sense. This is a base with a slightly base, like, and there's more base than there is acid, so we're going to have a basic pH, a higher pH, right? Less acidic pH. Any questions about how to simplify the Henderson-Hasselbalch equation? Right? All you have to do is calculate the pKa. If there's more acid than base, decrease the pKa a little bit, and that's your pH. Vice versa for bases, POH, pKb, that sort of stuff. Okay. So this is where, like I said earlier, that's how you're going to be able to do pretty much all of the math that's going to show up on the MCAT, right? We're going to talk a little bit, maybe a little bit later about, let's say this says pH is equal to pK. So just to clarify, I'm not quite sure what you mean by that, but basically we are using the pKa as an estimation for what the solution's acidity is going to be, if that makes sense. We're not saying that the right. So we calculated pKb, which gave us POH, right? But that's not what the question I gave is looking for. The question that I gave, we're looking for pH, which is going to be we have to use this equation right here to flop that into pH, if that makes sense. So basically, since this is a base, we're using the base version of the Henderson-Hasselbalch equation, if that makes sense. Then once we calculate the POH, all we have to do is throw it into that conversion. pH plus POH is equal to 14, right? So basically for these systems where you have both a little bit of conjugate acid and base, the pKb and pKa are just the starting point. That's where we're estimating the pH to start off at, and we're using the actual concentrations to actually estimate up and down from there. Does that make sense, Dylan? So like the pK and pKb, that is a constant for that acid at that temperature. We're using that to estimate what that's going to do to the solution around it using the Henderson-Hasselbalch equation. Definitely very confusing, but does that make sense? Gotcha. Okay, so is your confusion that like we used basic stuff and then somehow we ended up with an acidic number like pH? Okay. No, like I said, I just want to make sure that you understand this. That's why we're here, obviously, right? Um, so is the confusion just like how did we get from pKb to pH? Because like I know we talked about earlier how like that yeah, it basically equals, yeah, they're going to be really similar essentially. For these weak acid and base systems, the pH of the solution or POH is going to be very similar to whatever the pKb is, if that makes sense. Very close. But just since we have a slightly different concentration of acid and base, it's going to be up or down a little bit. Does that make sense? Basically, yeah, you can eyeball it. Yep. That's more than good enough. If you can do what I did here, you're going to be perfectly fine. Calculate the pKb. If there's more base than acid, decrease the pKb a little bit, and that's your pH, POH. Then you have to flop that into pH. Yeah, you can absolutely eyeball it. Right. Like I said, this is going to be stuff that we're using for like neutralization reactions, mostly like buffer systems, whenever they give you the concentration of an acid and its conjugate base or vice versa. Right. So pH and pKa are not the same thing, but for these buffer systems, whenever they give us concentrations like this, they're going to be very similar, just because the acid is going to be creating a solution that's very close to its pKa, and you can eyeball it like you asked. So, moving on, this is where we're going to start putting everything together, right? So, protonation versus deprotonation, right? Protonation is this idea that a species can gain a hydrogen, whereas this occurs. This will make sense here in a second. I'm going to use an analogy to make this a lot more simple. This occurs when the pKa of an acid is higher than the pH. Because remember, a low pH means that there's a lot of hydrogens. A lot of hydrogens present in those solutions, so those hydrogens are going to be thrown onto a lot of things. A lot of stuff is going to be protonated. And like I said, we're going to use an analogy to make this way easier to understand here in a second. So deprotonation is just the opposite. It's when a species loses a hydrogen. That happens when the pKa is lower than the pH, right? So just to make this much more simple, we're going to talk through an analogy where basically I want you to imagine that the temperature of your room is the pH, right? This is like the solution around you. You have a given pKa. This is the temperature that you like to put a coat on, right? Like we're all different people. I love being cold. I'm okay being like, for example, like if it's 65 degrees outside, I'm perfectly okay not having a jacket. Where like my sister, for example, she's wearing a jacket the second it's like below 80. I will add the clarification. We live in Texas, so like anything below 80. Yeah. For me, that's yeah. I mean, I live in Dallas, which is not in the grand scheme of things, it's not that bad. And obviously, like if you live in Arizona, you're used to like that really dry, crazy heat that it gets up to like 120. The hottest I've ever been in is Houston. It was like 85 degrees, but it was 100% humidity. That was the worst day of my life, even to this day. Long story short, what I'm trying to get at is like your pKa is specific to you, just like it's specific to acids, right? That's the temperature that you want to put a coat on. So a protonation is like putting a coat on. It's like putting a hydrogen on. You're grabbing another hydrogen. A deprotonation is like taking that hydrogen off, right? So we're going to be protonating at lower temperatures, lower pHs, and deprotonating at higher temperatures, higher pHs, just to keep with this analogy going, right? So if I basically put this temperature on a scale where it's decreasing to the left and increasing to the right, let's just say that there's a person who's okay with the cold that they don't need to put on a coat until like this temperature right here, a pretty low temperature, right? So basically above this temperature, they're going to have their coat off, which is why it's green, deprotonation. Above this temperature, above this pH, they are going to be deprotonated. Below this temperature, they are going to be protonated, right? For someone else who's much worse at handling the cold, their point in which they put that coat on whenever they get protonated or deprotonated is going to be much different. It's going to be at a higher temperature, a higher pH, right? Where above this temperature up here, it's a much higher temperature, a much higher pH. They are going to be putting that coat on. They're not going to take that coat off until it's a much higher temperature. Like I said, my sister doesn't take. She's like sweater weather is below 80 for her, which we've got a little bit of a cold front because of like the hurricanes that are going through, kind of the East Coast and everything. That like the high next week is low 80s, which for us in August that's kind of weird. We're not really used to it being that low. And my sister was kind of joking that she's gonna have to start wearing sweaters. Right, I wear sweaters because it's inside, and I keep my apartment like 68, but not important to what we're talking about here. But basically above this temperature, they are finally going to take their coat off, but below it, they're going to keep their coat on, right? They're protonating themselves. They're putting that coat on, right? If I actually convert this into the analogy with pH and pKa, the pH is like the temperature of your room, where the lower it is, the colder it is. So you're more likely to put on that coat at a low pH. You're less likely to put on that coat at a high pH, right? So let's just say, for example, there's an acid with a really low pKa. Its pKa is way down here. something at like 3, something like that. That means that below this pKa, whenever the pH is below this pKa, it's too cold. So it's going to put that code on, it's going to get protonated. Above this pH, it's warm enough for this pKa, it can take that code off, it's going to get deprotonated. Likewise, we can do the exact same thing with the higher pKa. The exact same conversation. If it's a high pH, high temperature, this thing is going to want to take that code off. If it's a lower temperature, it's going to want to keep it on, if that makes sense. But so basically, that is what pKa is telling you, is based on the solution surrounding this acid or base, it is telling you when that acid is going to act. So for example, HF has a pKa of 3. So if the pH were 1, is HF really going to be able to deprotonate itself at all? If HF's pKa is equal to 3, but the pH of the solution around it is equal to 1, what is going to happen with that HF? Is it going to stay in that protonated HF form, or is it going to dissociate into H and like losing that the hydrogen ion? Which one do you think is going to happen if the pH is lower than the pKa? Is it going to be protonated or deprotonated? Totally okay if you guys don't know or don't want to answer, but so basically, and I know I'm talking through an example right here. We're going to talk about amino acids here in a second. When the pH is lower than the pKa, it's going to be protonated, right? Basically, using the same analogy, whenever the pH is lower than the pKa, that's like the temperature being lower than what you're comfortable with. So you're going to put that code on. You're going to put on that hydrogen. We call that protonation, right? If that pH increases to like 7, then it's warm enough for that HF. It's okay taking that code off, deprotonating itself, disassociating into H ions and fluoride ions, right? And we're going to keep revisiting this analogy here as we keep going through amino acids, especially, right? This is one of the really important things that we get to talk about with protonation of different molecules. So I will give you all of the pKa values for the backbone of the amino acids, the carboxyl group right here and the amino group. Right, that's the constant. So this amino group, its temperature that it's okay with is 9.5. It's pretty high. This carboxyl group, the temperature that it's okay with is pretty low. They have 2 different ones, right? Technically, the R groups, if it's an acidic or basic amino acid, it can have a third one. We call those the ionizable amino acids. So if I throw this pH scale up here and kind of do the same thing that we just did, right? We are going to start off here at a pH of 2, trying to understand what happens at a pH of 2. So at a pH of 2, when we're first looking at the carboxyl group, if I go below that pH of 2, it is too cold for this carboxyl group. So it's going to keep its proton on. It's going to stay protonated, right? This H is going to stay here. And therefore, we say that this carboxyl group is neutral, right? Just like this, whenever it's protonated, it has this hydrogen, it's neutral. So the carboxyl group is protonated whenever the temperature is less than 2, whenever the pH is less than 2, which also means that it is going to be deprotonated or charged, giving up this hydrogen whenever the pH is greater than 2. One thing I will add is that whenever the pH is at 2, it's a 50-50 split. Half of the carboxyl groups will be deprotonated, half of them will be protonated. We'll talk about that later. Now, whenever we talk about a pH of 9.5, the carboxyl group, we've already figured out what's happening. It's going to stay deprotonated this entire time. But whenever the pH is equal to 9.5, this is where we get to look at the amino group, where below a temperature of 9.5, it wants to put its code on, right? It wants to, what is going on here? I'm just looking at this picture. This picture looks weird. Basically below a pH of 9.5, it is too cold for that amino group, so it's going to put it on, right? It is going to be protonated. Oh, no, never mind. I had it right. It is going to be protonated in this form with a positive charge whenever the temperature is colder than that pKa. The pH is lower than that pKa. Whenever it heats up, whenever that temperature increases, the pH goes above that 9.5, it is going to be deprotonated. It can finally take that code off, right? And so notice here, with this amino deprotonation. It was protonated right here and had that positive charge. It is deprotonated over here, and now it's neutral, right? So you could probably get away with understanding these two bits of information for the MCAT and probably be fine. But this is the exact same stuff that's going to help us really understand what's going on with like acids and polyprotic acids and stuff like that, even like conjugated systems as well, right? So I'm hoping that that analogy with temperature in your coat makes a lot more sense. Hydrogen is the coat, temperature is the pH, right? When the pH is really low, the temperature is really cold. You want to put on your coat. You want to put on your hydrogen. Burning biochemistry book. So the Kaplan biochemistry, but are you just saying that just because like you felt like it didn't help you understand that whole thing between pK and pH? Okay, gotcha. Yeah. Um, that's basically just the way that I had to understand it. Like you'll see that a lot of these things I have to put into my own words, right? Like those analogies with like the common ion effect. The textbook definition of common ion effect is when a like ion is contributed to the same solution, the solubility of both of those ions decreases. That does not mean anything to me. The analogy of the common ion effect, that like you're trying to put you have two people trying to put the same thing into the solution. So neither of you are going to be very good at it. You're both going to kind of have to stop too early. That makes more sense to me, right? So the same stuff like this right here. And so we'll, like I said, we'll keep revisiting this analogy here. I'm going to try to speed up a little bit because I don't want to, we still got a decent amount of stuff that I want to cover, and I don't want to hold you guys longer than the 4 hours. I will, even if you want to leave at the 4 hours, like I'm going to keep going until this is done. But yeah. So basically, like I said, in other words, put it more plainly, the amino group is going to take off its coat whenever the temperature or pH is above 9.5. It's hot, so it's going to take it off, deprotonation. For the carboxyl group, it is going to take off that coat whenever the temperature or pH is above 2, right? That's how we can get where the pH, when the pH is 7 at physiological pH, we know that the amino group is going to be protonated and the carboxyl group is going to be deprotonated because of the pKa of each of those things. So moving forward, we get to talk about buffer solutions really quickly, right? We talked about a lot of really big ideas. We're going to kind of be able to kind of quickly jump through some other stuff here. So a buffer solution is simply the combination of a weak acid or base and its conjugate, right? Typically in equal concentrations. Technically, it can be a little bit off here and there. But what this does is, since we have an acid and a base present, we can basically be resistive to pH changes, right? So like I said, it's composed of a weak acid with an equivalent amount, typically. It's usually close enough that it's fine, with its conjugate base, right? We're technically not adding like NaOH plus HCl. It would be adding NaOH with Na, if that makes sense. So we're not like creating like a neutralization where we're creating both hydrogen ions and hydroxide ions. It's an acid and its conjugate base. And we're using weak acids here, not strong, right? Those are the two characteristics. It has to be weak, and we're including an equivalent amount of its conjugate, right? So for example, if we take acetic acid has a pKa of 4.5. Its conjugate base, which is what's called acetate, anytime you see 8, that ending 8, it's a carboxylic acid that's been deprotonated. So we've just lost that hydrogen. So whenever we put these together into a solution with equal concentrations, that is a buffer solution, where basically in acidic conditions, when the pH is below 4.5, the conjugate base can act because it can accept a hydrogen ion to resist that acidic pH change, right? Anytime this solution becomes more acidic, the conjugate base can start interacting to kind of revert that pH change a little bit. Vice versa for if the solution becomes more basic. If the solution becomes more basic, then the acid can then go through and donate a hydrogen ion to resist that pH change. Right? That's basically just how buffers work. And by definition, they're going to work best whenever we get them to have a pKa around the desired pH, a pKa that is +1 or -1 from the pH range, if that makes sense. So if our reaction is mainly running at a pH of 2, and the buffer solution that we add has a pKa of 5, that is not going to be helpful, right? But if the pH of the reaction is going to be somewhere around 2 and the buffer solution is right around 2, then that's going to be helpful, if that makes sense. Like the pH of the blood. We want to keep the pH of the blood right around 7.35. So therefore, the buffer that we use, which is what's called bicarbonate, the bicarbonate buffer system, that buffer system has a pKa of around 7.4 because that's going to be the range that it works best at, right? So basically, if you can just define a buffer solution and know when they're supposed to be working, you're going to be fine. And to calculate pH, Henderson-Hasselbalch equation, like we talked about earlier. Okay, we're going to take another break. It's been another 55-ish minutes. We're going to take a quick 5-minute break, and then we're going to come back. We're going to finish up with some other last-minute stuff. The video for this, so the recording for this is, it's probably going to take, like I said, it usually takes Zoom about 6 hours for every hour. So just sometime around tomorrow night is when the recording will have been processed, because it does a lot of different stuff. It will like create like a transcript and stuff like that, and also just has to like go back and record the video. So just FYI, I'm gonna go and start the break timer right now. We'll start at 10 minutes after again. But yeah, basically the email will be, the recording will be pushed out sometime tomorrow night or early, what is I don't even know what day today is. The day after, Thursday, sometime on Thursday, just depending on whenever the recording is finished. And I'm also going to make sure that that Anki deck that accompanies this is finished, so that I can send both of those together and you can review them as quickly as possible. I'm probably also going to either put this entire recording or put it up in bits and pieces on YouTube. I'm probably going to start off with bits and pieces, where basically like the analogies that I use for like the common ion effect and complex ions and like the pKa, pH, deprotonation, that is all. Yeah, sure. I don't mind uploading the slides. Yeah. Yeah, all of that stuff. I'll probably just upload the slides to my website. But yeah, that's all of that stuff. I'll add that to my list of things to do. I can do that throughout this week. But this in either in pieces or in completion will be up on YouTube at some point, publicly, which, like I said, all of your information is not, it's, I have it set to where nothing is included. Right. Yeah. Anki deck, the entire recording, that stuff will be emailed by sometime on Thursday. Hopefully tomorrow night. It just depends on when the recording's done. I finished the Anki deck about 20 minutes before the lecture started, before I hopped on. So that's all ready. I just have to wait for the recording. I don't want to send multiple emails. So yeah. Okay. All right. I will be right back. Like I said, 10 after is when we're going to pick up. Yeah, of course. Yeah. I'll be back in a few minutes. All right. I know that was like a quick break if you stayed after to listen to me talk about the recording. And I was going to try to take a little bit of a longer one, but we still have like 16 or 17 slides to get through. And I just want to make sure that I'm not, like I said, keeping you guys. I know I said that I would try to keep it around 4 hours. That was an estimate, which I think I'm going to be really close to. It's one of the only things I've ever been proud about myself in my life, apparently, is my time estimation skills. But like I said, I'm going to try to keep this pretty short. Again, I'm gonna explain everything that you need to know. I'm never gonna cut that short. I'd rather go long and make sure that you guys understand everything rather than stopping short and just for the sake of time. But I'm gonna try to make sure that we go through this quicker rather than slower. But with that being said, we actually don't have that much to do left. There are a few confusing topics for us to talk about left, and then we do get to talk about the lab techniques, but that's pretty much where we're going now at this point. We have a few things to talk about with pH and pKa, then we get to the lab techniques, and then we're done for the day. All right, that's everything you need to know for acids and bases on the MCAT. So basically where we are going to pick up is applying everything we just talked about with protonation and deprotonation to the polyvalent acids and bases, right? So make sure you remember those protonation rules, right? So for example, when we're talking about HF, if the pH is below the pKa, like when it's really cold, it's going to be protonated, right? So that would be at a pH that's less than 3.2. If the and like I drew the arrow pointing really big in the protonation direction, which is HF. HF is the protonated form. Whenever the pH is equal to half of the pKa, so that acid is going to be half protonated and half deprotonated. Right? This is something that I didn't fully express whenever we were talking about it earlier, but by definition, when the pH is equal to pKa, so whenever the pH is equal to 3.2, half of it's going to be protonated as the HF form, half of it's going to be deprotonated as the F minus form. This is kind of like, for example, using my temperature analogy, this is literally like the temperature where it's like if you were standing still, you would be cold, but then the second you start moving, you have to take it off, if that makes sense. It's like a 50-50 decision. That's whenever pH is equal to pK. Temperature is equal to that temperature. You want to keep that coat on or off. And then finally, when the pH is equal to the pKa, sorry, this is supposed to say greater than. Let me. I need to edit this real quick. That's a bad typo. Give me 1 second to edit this really quickly. You get to look at my lovely background while I fix this really quickly. Okay. Then whenever the pH is equal to the pK, that's the advantage of you guys being in kind of on the ground floor of this, is you get to catch my mistakes with me. I went through and gone this lecture already, but like there's still a few things like that. As you can imagine, I have enough notes in here that there's a few things that sometimes slip through the cracks. But basically, whenever the pH is greater than that pKa of 3.2, it's too hot. It's going to take off that coat. We're going to promote that protonated state, which is the fluoride ion. Right? Okay. So we're basically going to be able to use this. We already used it to predict when a specific acid is going to be protonated or deprotonated, but we're also going to be able to use it for polyvalence as well, right? Because like we talked about earlier, polyvalent acids and bases are going to have multiple pKa's. So they're going to have multiple different places that they're trying to decide if they're going to take off another layer or not. So for this example right here, phosphoric acid is added to a solution with dissolved KBr. That's just the salt that like it's inert. So we're not going to worry about that right now. And the question is asking which protonation state is going to be most present in the blood, right? So there's 3 pKa's of H3O that they're giving to you. It's 2, 7, and 12. So let's just go one by one, right? So whenever we list out the different forms of this acid, where this is there's 3 protons here, it's lost a proton here to become H2, it's lost another proton right here to become 1 hydrogen, and now it's fully deprotonated at this point. Remember, protonation is green, that's always going to be to the right. Deprotonation is red, that's going to be, protonation is red, that's to the left. Deprotonation is green, that's to the right. I think that's what I just said. I can't remember. And then we can fill in all of these pKa's for all of these arrows, right? That's what this means. Whenever they tell you these 3 pKa's, it's saying for this first reaction, it's occurring right around a pKa of 2. The second one is occurring at a pKa of 7. Third one's occurring at a pKa around 12, right? So at a pH of 7, phosphoric acid is going to exist as 50% of this diprotic form and 50% the monoprotic form. All right, that's at a pH of 7. That's what this pKa right here is telling us. But physiological pH of the blood is slightly above pH of 7. It's like 7.4, 7.35 technically. So because of that, it's going to slightly be on the basic form, the slightly deprotonated form, if that makes sense. So the most common form of phosphoric acid that we would see in the blood is HPO4 2-. We can easily predict that just by understanding this relationship between pH, pKa, protonation, and deprotonation, right? pKa right here, this is a 50-50 split at 7, whenever the pH is equal to 7. We've gone a little bit more basic than that, so there's going to be slightly more deprotonation. We've convinced this H2PO4 to give up another hydrogen to become HPO4 2-. So as we talked about earlier, if there are any ions in solution, those ions can just form one of those interactions. It's not a reaction, but it's an interaction, meaning it's a positive interacting with a negative. It can form a salt bridge, an ionic bond to this negatively charged molecule right here. Right? We're not forming a reaction. We're not reacting with water at all, but we did put KBr in that solution that the K is going to have a positive charge. The Br is going to have a negative charge. So those potassium ions can basically just, as they're going around, if they see a negative charge, they're going to be attracted to that charge. It's not a stabilization or anything like that, but basically just because of electrostatic attractions, we can get some of that negative charge from this ion right here attracted to the positive ions from potassium. And basically that's what we see. Because HPO4 2-, it is because it's unstable. That's not necessarily important for what we're talking about right now. It might associate with 2 potassiums to form K2HPO4, if that makes sense. So basically, if you see kind of a weird thing that it's like a conjugate base of a polyprotic acid that's all of a sudden associating with a metal, this is what they're trying to show you right here. that, okay, this is the protonation state. We're talking about this little state right here that just has happened to have associated with 2 potassium ions to stabilize itself. Right? Okay. The next thing that we're going to talk about really quickly is this idea of gram equivalents, right? By definition, this is going to be another one of those things that we kind of use a different analogy, right? By definition, a gram equivalent is the mass of a substance that's required to produce 1 mole of hydrogens in solution. Right. So, as an example, we're going to use kind of like layman's terms here. We're going to make this much more simple. Let's imagine that you were trying to get 10 bullseyes. This is the equivalent of trying to get like 1 mole of hydrogens. So, the number of shots is how many gram equivalents there are. And this will make sense here in a second. So, person A, they can throw 1 arrow per shot. So, that means it's going to require 10 shots to get 10 bullseyes, right? Basically, 10 gram equivalents. Person B can shoot 2 arrows per shot. They have some weird arrow contraption that they can shoot 2 arrows per shot. So it's only going to take them 5 shots to make 10 bullseyes. So because of that, if we're trying to get 10 bullseyes, person A has to do half as much work. We need half as much of person B. Person B is going to do half as much work, I meant to say. They only need 5 shots. So because of that, we can basically say that like we need less of B to make the same amount as A, if that makes sense. This is going to make more sense when we use like a real MCAT style example here. So basically, how many grams of H2SO4 are required to produce 0.25 moles of hydrogen ions, right? So H2SO4 has 2 equivalents. It has 2 hydrogens, right? Which basically means that whenever H2SO4, which is a strong acid, fully dissociates, it's going to form 2 equivalents. Sorry, I'm getting ahead of myself. Whenever it fully dissociates, it is going to form 2 moles of hydrogens, right? Whenever 1 mole of H2SO4 dissociates, which is 100 grams, it's going to form 2 moles of hydrogen ions, right? So because of that, in order to make 0.25 moles, I can just kind of keep working my way backwards. So if 100 grams of H2SO4 is 2 moles of hydrogen ions, that means 50 grams would be 1 mole of hydrogen ions. 25 grams would be 0.5 moles of hydrogen ions. 12.5 grams, we just keep cutting in half of H2SO4. That's going to get us to our 0.25 moles of hydrogen ions, if that makes sense. Basically, what I'm trying to get at here, just to simplify this, is just throwing the equations up on the board, right? Where if you take the number of the molar mass and divide it by the number of hydrogens the acid can donate, the number of equivalents that it has, that's going to give you the gram equivalents. Where basically H2SO4, we need half as much H2SO4 as we would some other monoprotic acid to make the same number of hydrogens. If we're trying to make 1 mole of hydrogens, we would need half as much H2SO4 because it has 2 hydrogens it's donating at a time. Right? If that doesn't make sense right now, it might make a little bit more sense when we talk about what's on the next slide, which is normality. Right? Normality is a very similar idea, but it's kind of going a slightly different direction. Gram equivalence is talking about the mass of the acid or base that we're talking about. Normality is talking about the hydrogen concentration that's produced. It is the concentration of hydrogen ions that's produced whenever a species is put into solution due to its number of equivalents. Right? So just as an example, again, another like layman's terms, simple example. Imagine that we're talking about the total number of snowballs that you're throwing here. That's the same thing as normality, right? Person A can throw 1 snowball at a time. So for every 10 throws, they get 10 snowballs. For every 10 moles of acid, they get 10 moles of hydrogen, right? This is like a monoprotic acid. Person B, they can throw 2 snowballs at a time. So for every 10 throws, they actually throw 20 snowballs. This would be like a diprotic acid, like H2SO4, that basically for every 1 mole of acid, we end up with twice as much hydrogen, right? Basically, person A has a smaller normality than person B. Normality is basically a concentration that just takes those equivalents into effect, right? With that, remember earlier, we already did this with acid and base math. We already did this with that calcium hydroxide question where there was 2 hydroxides. So because of that, we had to double the concentration of calcium hydroxide to get the hydroxide concentration. That's normality. That's what normality is. Right? Just to give you like a real MCAT style example, they might ask the question like, which of the following acidic concentrations or conditions, whatever you want to say, would have the lowest pH? Basically, the highest hydrogen ion concentration, right? So A says a 0.8 molar concentration of HF. So HF is monoprotic and it is a weak acid. So that's probably not a great answer. I'm going to leave that in red for now. That's probably not what we're going to go with. H2SO4, the concentration is lower, but that's a strong acid, right? So we'll come back to it. That sounds like it's probably going to be a good answer choice. Same thing with HCl. We have 0.4 molar concentration of HCl. That's a strong acid. That's going to fully dissociate. D says 0.3 molar of a triprotic, meaning 3 hydrogens, phosphoric acid. So while this has 3 hydrogens to donate, it's a weak acid and it's not going to be very good at fully dissociating. We're not going to get all 3 of these hydrogens off of it. So basically our best answer choices are B and C, right? But let's look at normality. So C is a 1-to-1 ratio. For every mole of HCl that dissociates, it's going to produce 1 mole of hydrogen ions. That means its normality is 0.4. If we do the same thing for H2SO4, the normality, which is the hydrogen ion concentration, is 0.8. So therefore, because of that, B is going to be the best answer. We're looking for a strong acid with a high normality, because that normality is going to tell us the hydrogen ion concentration. That's what we care about when we're talking about pH. Right, so then just the simple equations for normality. Normality for an acid, it's the acid concentration times its number of equivalents. So H2SO4, its concentration was 0.4. It has 2 equivalents, so its normality is 0.8. The higher the normality for acids, the higher the acidity. That is more acidic, lower pH. And this also applies to bases as well. We can take the normality for bases would be the base concentration times its number of equivalents. So like calcium hydroxide has 2 equivalents. So we'd multiply the concentration of calcium hydroxide by 2 to get the normality, if that makes sense. And that's what we use to actually calculate pH for hydrogen and hydroxide. Okay, we're going to keep trugging along. Like I said, we're getting kind of close to the end here. We have a few more small things. I have some tips for math. I'm going to kind of skip over my math example problems until we get to the end. And then just based on what time it is, if you guys want to stick around, I'll go through the math example problems. But if not, what I'm going to do is I'm just going to do those at the end of the lecture and they're going to be on the recording. That way we get through all of the content that you need to know. And then if you want to see an example problem, you can just watch the lecture later. So we're going to talk about indicators really quickly. So an indicator is basically, it's kind of similar to a buffer solution, that it's going to be a weak acid or a base. But instead of its job being to resist pH changes, what it's doing is it's changing colors depending on the pH of the solution. It's reacting to the pH of the solution to tell us what color it is reacting to the pH of the solution by changing colors. And therefore, when it changes colors, we know that something happened, essentially, because the pH is changing. So for example, like if we have like a weak acid that we're using as an indicator, maybe it is, whenever it's put together, it is red, right? And so this is the protonated form. This would be at like a low pH. But then eventually, once we get past the pKa of this indicator, it's going to dissociate into its conjugate base, which maybe is purple. So therefore, we now have something that we can use to tell us when a reaction has gone past a certain pH, like when a reaction is complete, when a neutralization is complete. So they can essentially be used to determine when a neutralization has been completed. Some sort of acid-base reaction has been completed because they're going to tell us what that pH of the solution is going to be at, if that makes sense. So just as an example, let's just say that there's this neutralization reaction that we're trying to run, that it's supposed to be done whenever the pH reaches 9, whenever it gets above 9, right? So for example, there is this indicator called thymol blue. It is a weak base that it appears yellow in its conjugate acid form below a pH of 9. And in its basic form at a pH above 9, it is blue. So basically, if we're trying to monitor when this neutralization reaction has completed, all we have to do is look for when thymol blue turns blue. because that's telling us that the pH has gotten above 9 and this neutralization that we're talking about right here in this example has been completed, right? They're basically just spectating the solution, telling us when the pH has changed, and therefore that will help us know when the reaction's been complete. So likewise to how we wanted to pick a buffer solution that was plus or minus 1, that had a pKa that was right around 1 around the pH that we're looking for. It's the same idea for the indicators. We want the indicator to have a pKa that's within plus or 1 of the expected reaction completion pH. So like, for example, if you expect a reaction to complete at 9, you don't want to pick an indicator that has a pKa of 2. That's not going to help you at all. You want to pick a pKa that has an indicator of like 8.5 or 9 or 9.5, just whatever's closest to that expected pH. Okay, moving forward, like I said, this is where I'm basically just going to provide some quick math tips. Right, I'm going to provide some quick math tips just to hopefully make your life a little bit easier. This is all going to be stuff that in my YouTube videos that are really separately from this. They're also going to kind of explain a lot of the stuff that's mentioned in here. But so basically just how to make acid and base easier. I've created a flow chart where essentially all you have to do, basically what I recommend doing is keep this open next to you. And so whenever you keep this open next to you, whenever you're doing your acid and base math practice, what you have to do is just identify where you're starting off at. Identify where you're starting off at and then follow the arrows in order to get to where you're hoping to end up essentially, right? So we're going to start off with the very basic stuff within dimensional analysis. Grams, molar mass, and moles, right? This is not exclusive to acids and bases, but I'm just clarifying here that we're talking about the acid and base weight in grams. So we can easily convert the acid and base weight in grams to its molar mass, right? I mean, that's given on the periodic table. And then we can also immediately convert that into its number of moles as well, right? That's a really easy thing to do. All you have to do is basically just cancel out units until you're left with moles, or you can go the reverse direction. It's basically just telling you the order that you're supposed to be going through each thing, right? Once we get to this number of moles, this is where basically what I'm going to say is where you should do your stoichiometry check. This is where you're trying to check for like number of equivalents, essentially, where if something is a diprotic acid, that means you're going to kind of have to change what you do for the rest of this, convert it to normality instead of just rocking with the acid and base concentration, right? So that's just a really good place to check your stoichiometry in general is whenever you get to moles, right? Because all of chemistry is a mole to mole reaction, not a concentration to concentration reaction. Things are reacting on a mole to mole basis, right? So the first place that this is actually going to diverge is whenever we have one of those kind of like neutralization reactions where basically, or like buffer solutions that you're adding any acid or base. You're adding any acid or base together. I'm going to add that note right really quickly, that this is also like buffer solutions. So all you have to do whenever you get to buffer solutions is figure out the number of moles of hydrogen or hydroxide that there are, and then plug that straight into the Henderson-Hasselbalch equation. You can convert that into concentration if you wanted to, like hydrogen concentration or hydroxide concentration, because that's essentially what the acid concentration and base concentration in the Henderson-Hasselbalch equation is basically telling you. So you can use those interchangeably. But basically, this is the scenario that you're supposed to be using that Henderson-Hasselbalch equation. Is anytime there's a neutralization, you're trying to figure out what pH that neutralization happens. You're going to use that Henderson-Hasselbalch equation as well as the pKa of the acid or whatever base that you're using to calculate the pH, right? Anytime you have a neutralization or a buffer solution, you're going to figure out how many moles of hydrogen or hydroxide, moles of acid or base, same thing. You're going to use the pKa and pKb with the Henderson-Hasselbalch equation to calculate the pH or pOH, right? Then from there, that's how you calculate weak acid base questions where they give you a concentration of an acid and a base. Like I said, like neutralizations or buffer solutions. From there, you can use any of these acid base conversions to go any direction you want. Like maybe they ask you to solve for pOH, but they only gave you the information to solve for H, right? Basically, what I'm trying to get at here is you can use these conversions over here at any time. Anytime you calculate pH, you can turn it into pOH. Anytime you calculate pKa, you can turn it into Ka using this rearrangement we talked about earlier. Same thing delineating between Ka and Kb. So this is another thing that, just so you know, make sure that if you're working with acids, but they ask for a basic quantity, you swap it at some point. And anytime you have one of these quantities, you can change it really easily. That's what these are used for. They're used to change from one thing to the other, if that makes sense. So the other scenarios is when we have a weak acid or a base or a strong acid or base. Those are the other scenarios that you're going to have to do math with. So basically from here, what you're going to do, like I said, you want to do a normality check. But once you have that concentration of the acid or base, what you can do, you need the volume to go from moles to concentration, because concentration is moles divided by volume. But basically, once you can do, we'll start off with the weak acid and base. This is a scenario where they've only given you the concentration of the weak acid or base, the weak acid, essentially. Not they've given you both. If they've given you both, this is the path that you're going to follow. But if they've just given you one or the other, you're going to take that concentration, you're going to use that Ka or Kb value that they would have given you, and then you're going to use an ice table to calculate the hydrogen or hydroxide concentration. Then from there, you can just plug it into that rearranged equation, 10 to the power of negative pH is equal to the hydrogen concentration, to get your pH or pOH. And from there, you can convert anything to whatever. Maybe they asked for pOH, but they gave you information for pH, right? Basically, like, I'm hoping you can see that this is literally just like a flow chart. It's kind of like a guide of instructions of like, this is how you get from point A to point B, right? There are going to be some complex questions that it's a little bit more complex than what I have here. But for most of your questions, this is going to be kind of a step-by-step guide that gets you through pretty much every single question, right? So then if we have a strong acid or base, all we have to do is we have to take the acid or base concentration, make sure that we get the right hydrogen or hydroxide concentration by checking normality, and then just plug that straight into the pH or pOH equation. Right. So this is a figure that I haven't put into the notes yet. I forgot to do it. Essentially, I gave myself the note to do it, but I just forgot to do it. So I will add that basically right after we're done here in that set of notes that I've added. But like I said, I recommend just keeping this up next to you whenever you're doing math problems, and then that way you can basically just go step by step, essentially. And this should make it easier to start building that pathway in your brain. If like, okay, this is where I'm starting, and this is how I get to where I need to go. Right? Because I feel like that's one of those things that often happens is like they'll give you the mass of an acid and then they ask for the pH. And you're like, I have no clue how to get there. Right? But this is basically showing you, okay, you get from grams, the first thing you need to do is somehow get to concentration. So you need molar mass, moles, and volume in some way, right? And then from there, if it's a strong acid or base, you just go through this right path and you're done. Okay. So the other thing that I was going to say was just some other general math tips. So in general, like I said, I have a video that's going to talk about using scientific notation. That's going to make scientific notation much easier to use. In fact, that one's already out. You can already go and watch that one. Scientific notation makes the math so much easier on the MCAT. Sounds counterintuitive, but it really does, I promise. So if you can't do the math simply in your head, turn the numbers into scientific notation. Always check to make sure that your units are proper of what they're supposed to be in. Like, for example, if they gave you milligrams, but the answer choice is in grams, you got to convert it, right? There is one exception to that. That's going to be answer choice number three or four. But you'll see here in a second. But likewise, like another example of that is if they gave you pKb, but ask you for pH, you have to convert that pOH into pH. Like, don't just solve for pOH because they gave you the pKb and then say, oh yeah, I'm done. You got to make sure that you're actually getting to where they want you to go, if that makes sense. So units are really important. I also recommend looking at the answer choices before doing any math. And like I said, I don't have the time to go through this example, but I had a pretty complicated math example on this next slide that's actually going to be quite a bit easier because I just added a whole bunch of acids to a solution and I asked for the pH or pOH. I can't remember which one. But if you only have acids present, the pH is going to be low, below 7, right? The pOH would be above 7 in that regard. There were two answer choices that had a basic pH. So you can immediately get rid of those because you're adding acids to the solution. And then maybe from there, one of them is completely wrong and the other one at least makes sense. So basically what I'm trying to say is even though you might have some complicated math, you can at least start eliminating answer choices just on the basis of understanding and like having an expectation for if it's supposed to be acidic or basic in this example, right? Always make sure that you're checking for stoichiometry. If it is a polyprotic acid, you got to work with normality, right? Stuff like that. You got to make sure that equations are balanced as well. There's no guarantee that if they give you an equation, it's balanced. I usually make sure to go through and check it. And then finally, the last thing that I was going to say is kind of a little bit the opposite direction of two. But if you get to answer choices and every single answer choice has a completely different number at the start of it, like A is 1.3 times 10 to the negative sixth, B is 7.4 times 10 to the negative 12, C is 2.8 times 10 to the negative 19th. You actually don't have to worry about the scientific notation or number of zeros. Because basically, the number of zeros in scientific notation is only going to affect how many zeros there are. It's not going to change that number that's out front, that coefficient. So you can basically just do the math without doing a whole bunch of those crazy conversions of like milligrams to grams. And just as long as you know that, for example, let's say you end up with 300 grams, but one of the answer choices is 3 grams. That has to be your answer, if that makes sense. Like, sure, you're off by a factor of 10, but your coefficient is correct. That's a little bit harder for me to explain right now. Like I said, I'll have videos coming out about that. And whenever I go through and do those example problems, as soon as we're done at the end of lecture, you'll kind of see what I'm trying to get at. A little bit. But yeah, and like in those next two practice problems, there's a lot of examples of this. Like I said, this is not supposed to be a math lecture for the most part. Specifically for acids and bases, yes, but not like a holistic MCAT math thing. That's why I'm going to kind of hold off on explaining all of this. But so we're going to skip over these problems for now. Like I said, I'm going to stick around and do them when we're done. You don't have to be here if you don't want to be here. Obviously, I mean, this is a free lecture. You can do whatever you want. We're going to skip really quickly through this break because we actually don't have that much left. I don't know why I was planning on taking a break there. But we basically just have the lab techniques left, and this should be relatively quick. So I will take a little bit of a second to kind of debrief everything that we've talked about. Basically, we started off just defining the types of acids and bases. Then we looked through the different properties of acids and bases, right? Like polyprotic, what complex ions do to acidic salts and basic salts, a whole bunch of stuff like that. We talked about what K is, which that's just a measure of how good of an acid something is. We related that to pKa, and then we used that pKa to understand when that acid is going to be protonated or deprotonated by looking at pKa versus pH, right? That's the roadmap of basically everything that we've done, which is a lot, right? We've been lecturing here for 3.5 hours, which I mean, hopefully this is like the last time you ever have to watch like an acid and base lecture outside of like going back and reviewing an individual piece. But basically, where this has led us to is hopefully now at this point you understand how to answer pretty much all of those questions that are just talking about like here's how do you calculate pH, or if I add this complex ion, what is that going to do? Complex ions increase acidity or base acidity of salts, stuff like that. The last little leg of pH and POA of acids and bases is just like the lab techniques. This is usually considered like like this will fall under either, if you know like the AMC skills breakdown, it's skill 3 or skill 4. Basically the AMC has a different types of questions that they try to have, like for example, I think full length 1 has 6, skill 3, which that's like knowing lab techniques, that kind of type stuff. This is basically where that stuff is going to kind of fit in, where realistically you kind of just need to know what each lab technique is doing and just a little bit about how it works, right? So there's 3 lab techniques that we're going to talk about pretty quickly. The first is litmus paper, that we use that to determine the pH of a solution. The second is isoelectric focusing. This is going to tell us when a protein is charged or uncharged based on a pH gradient gel that we're going to use. And then the final is titrations, right? That's the one that I think is usually pretty confusing, but for the most part, the MCAT's going to keep them simple. They get kind of complex when we talk about polyprotic titrations, which I will cover them, but realistically, there's only really one thing you need to be able to do with polyprotic titrations, and I'll explain that whenever we get there. So the first thing that we're going to talk about is litmus paper. So litmus paper, for every single type of litmus paper, what it does is it turns, that paper will turn red if there's an acid, like if it's an acidic solution. It's going to turn blue if there's a basic solution, right? That's what they do. They tell you how basic the solution is based on how red or blue it is. So there's what's called universal litmus paper. They're not necessarily going to use this word universal. In fact, you don't really even need to know the different types of litmus paper. Like this is going to pretty much get you to every single answer you want here. for all types, acids appear red and bases appear blue. But for for universal litmus paper, it can either identify the strength of an acid or a base, where basically it starts off as like kind of like an orange color. As it becomes more basic, it's getting closer to like a blue or purple, like we talked about right here. As it becomes more acidic, it gets closer to like a red or orange. All right, that's pretty simple. That's all you need to, if you see litmus paper, that's what it's doing. For red litmus paper, that is going to be identifying how strong a base is, if that makes sense. It's going to be a little bit more accurate for identifying how strong a base is, if that makes sense. So basically, it's red, meaning it's kind of starting off acidic, but it's going to turn blue depending on how basic that base is, if that makes sense. So it's still that relationship that if there's a base, it's going to appear blue. If you added an acid to red litmus paper, it's just going to stay red. Likewise, with blue litmus paper, it's identifying the strength of an acid. So the more red it turns, the more acidic it is, right? Here's two pictures of basically what that stuff looks like. But long story short, with litmus paper, as long as you know that it's going to appear red with acids and blue with bases, you're going to be fine for the MCAT. I wouldn't worry too much about trying to understand the vast differences between red and blue litmus paper. Okay. So the next thing that we're going to talk about is isoelectric focusing. So isoelectric focusing, like we talked about earlier, it's used to determine the isoelectric point of an amino acid, which that isoelectric point is basically just the pH of an amino acid that it becomes net neutral, essentially. It's kind of similar to the idea of what a pKa is. In fact, what it is, it's literally just the average of pKa's of a molecule. If a molecule has multiple pKa's, the pi is just the average of some of those pKa's, essentially. So basically, all amino acids, because this is used on proteins, essentially, all amino acids are going to have a carboxyl and amino group that are going to be protonated or deprotonated. We already talked about all of that earlier with this thing that we did earlier, essentially, right? I'm not going to cover all of that again. That's obviously in the recording. You can go back if you need to that little middle section. So for the uncharged amino acids, those are the only two pKa's that they have. So in order to calculate the pi, all you have to do is just average those pKa's, right? For the acidic amino acids, which are going to be negatively charged at physiological pH, they're anionic. What you're going to do to calculate the pi of the acidic amino acids is you just take the two most acidic pKa's, the two lowest pKa's, and then you average those. For the basic amino acids, you just average the two most basic pKa's, right? Which is going to be the amino group and whatever the R group, the basic R group, right? That's basically how you calculate pi, which, like I said earlier, pi is basically just the point where on average that amino acid is uncharged. So just to show you how this actually works, an isoelectric focusing, it's an electrolytic cell. Again, this is a redox gen chem thing. We're not going to dive into this right now. These are unfavorable, meaning that we're going to have to supply some sort of voltage. And because of that, we also know that the cathode is the negative terminal, which in this regard is going to represent a high pH. The anode is the positive terminal, which is going to represent a low pH. So whenever you put a protein into a solution, if it is cationic, meaning positively charged, it is going to migrate towards the negative terminal, the cathode, right? Basic proteins are cationic, so they're going to travel to the high pH zone. Acidic proteins, which are anionic, are going to travel to the positive terminal, which is the anode. This represents a low pH. Right? So if you can identify that a protein is acidic or negatively charged, you know it's going towards the anode, which is the low pH area. Just to show you kind of how this works, basically, if I put the isoelectric focusing gel up on the page, basically what happens is they all start off in the middle, kind of around like a pH of 6.5 or 7. We turn on the voltage, and these proteins start to move down that concentration gradient to wherever they're attracted to. Right? So the positive basic amino acids are attracted to the negative high pH terminal. The anionic negatively charged acidic amino acids are attracted to the positive anode. Right? So for example, protein A, notice it stopped at a pH of 9. So because it stopped there, it's now uncharged. It's not going to move in either direction. That means this protein has a pi of 9.2. It is uncharged on average at a pH of 9.2. Protein B stopped at like 5.5, so it's like slightly acidic or anionic. That protein is, so it would have a pi of 5.5. And then protein C is also anionic or acidic because its pi is 4.3, less than 7, meaning that it's uncharged at a pH of 4.3. Right? That's how we can figure out how acidic or basic amino acids are, how negatively or positively charged they are. We put them in this gel, they move based on this pH gradient. So because of their pKa's, some are going to be protonated or deprotonated. They're going to stop moving when they're uncharged. And so because of that, we can figure out how positively or negatively charged they are. Okay, again, as always, if you have any more questions, we've got literally a few more slides left, and then that's it for everything you need to know for acids and bases, Gen Chem acids and bases. The last lab technique that we're going to talk about is the illustrative titrations, right? These kind of suck, if I'm being honest, but basically what they do is they're trying to identify the pKa, like the identity of a acid, as well as its concentration. So there's a few components that make up a titration. There's the titrand, which is the thing that you're trying to figure out. You don't know what it is. There's the titrant, which is the acid or base that you're adding to learn more about the titrand. It's always going to be a strong acid on the MCAT, a strong acid or base that we're using to neutralize the titrand. So if you find out the titrand is basic, we're going to be using a strong acid. Then there is the pH indicator, because this is going to tell us when that neutralization is complete, which is going to help give us some other information. We'll talk about that later. And this is basically what the graphs look like. This is what a titration curve looks like, where on the y-axis, this is the pH of the solution. So we're just monitoring the pH at different times. On the x-axis, it's the volume of titrant that's been added. So usually they're going to give you the concentration of the titrant, like maybe they say it's 1 molar solution of NaOH. And then therefore you can calculate how many moles have been added using the volume, right? Because molarity concentration is equal to moles divided by liters. Whenever we're doing neutralizations, we care about equalizing the number of moles. So that's why this stuff is important here. We'll talk about that a little bit here in a second. So from here, just to kind of expand on this a little bit, the first point that we're going to look at outside of point one, basically point one is just telling you that the original thing, the titrand, is an acid. That's all it's telling you. pH is below 7, so it's an acid. Basically, the half equivalence point is this point right here, point 2. We also call it the buffering region because know it's being pretty resistive to pH changes. We have to add a lot of base to get the pH to change. Right? It's the middle of this flat region. The things that we can learn from this little flat region right here, we can learn that the pH is equal to the pKa of that unknown, of the titrand. So this acid that we're studying right now, it would have a pKa of around 5, right? Not a very strong acid at all. It's pretty weak. Additionally, this is just kind of a one-off thing. They're never really going to make you do too much math with this outside of just literally telling you, like, at point 2, if the original acid concentration is 1 molar, what's the conjugate base concentration? It would also be 1 molar. They're equal, and that's why we call this the buffering region. We have equal amounts of conjugate acid as we do base, or vice versa. The next point that we need to talk about is point 3. We call this the equivalence point. The equivalence point is basically the middle of this vertical line, and it signifies where we basically fully neutralize that original acid, that original titrand. So the things that we can learn from this point, we can learn what the pH, we can basically use the pH at this point to tell us if that unknown was strong or weak. Literally like a strong acid, meaning like HCl, one of those that dissociates fully, or weak, meaning it doesn't dissociate fully. So notice that this equivalence point has a pH of around 9. So because of that, we're going to be able to kind of learn what that means here in a second. We'll talk about that in a second. Whether the titrand of the unknown was a weak acid or base. Additionally, the number of equivalents of titrand, basically however many moles of hydrogen that titrand made, that acid made, is going to be equal to the amount of OH that the base made. Basically, this is a fancy way to say that the amount of hydrogen is going to be equal to the amount of hydroxide. The moles of hydrogen is going to be equal to the moles of hydroxide. Right? That's basically what's happening here at point 3, which we can use concentration and normality to figure that out. It's pretty simple. We'll talk about that in a bit. And the indicator that we're using to actually know when this reaction is complete is going to have a pKa at this point. So we would want to be using an indicator, a color changer that has a pKa of 9 for this one, because that's going to tell you this titration is done, it's been neutralized. Okay, so just to talk about this first point a little bit really quickly, if the equivalence point, like for example in this one, if the pH is greater than 7, that means we had a weak acid titrand that we titrated with a strong base. Weak acid plus strong base, basically the base is stronger than the acid is. So it's going to win. It drags the pH above 7. If the pH is lower than 7, that means we had a weak base that we titrated with a strong acid. And then finally, if pH is equal to 7, that means they were both strong. This would be like HCl, which is a strong acid, plus NaOH, right? So basically, the pH of the equivalence point can tell you how strong this original unknown thing was. It can tell you if it's strong or weak based on the pH of that equivalence point. The next thing that I wanted to kind of clarify is this second point about the equivalent stuff, right? So like I said, it's basically at that point, the number of moles of hydrogen from the acid is equal to the number of moles of hydroxide from the base, right? So for monovalent acids or bases like basically HCl and NaOH, stuff that only has one equivalent, all you really have to do to make this work is set the concentration of A times the volume of A, which what I will note is concentration times volume is equal to moles. So moles is equal to moles here. So concentration times volume of A is equal to the concentration of the base times the volume of the base. Right. Just to clarify, if they do throw for some reason a polyvalent acid in front of you, just know that you're going to be using normality instead of concentration. I highly doubt that that's going to happen. We can, if you have a question about that, we can talk about that. But yeah, from here, we're basically going to do an example, right? Where in this example, the titrant, which is the thing that we're adding, notice it's a strong acid here. They gave me the concentration and they gave me the volume of the titrand, right? So we'll go point by point, right? We know, and here's volume of titrant across the x-axis, pH along the y-axis, of course. Always look at your axes. So we know that the pH starts off at 11, right? The pH starts off at 11, so we know that our unknown of the titrand is a base. So we are titrating a base with a strong acid HCl. We also know that it is monoprotic. There's only one equivalence point here. This is something I'll clarify on the next slide. But because of that, it only has one equivalent. We also know at this half equivalence point, point 2, the middle of the buffering region, that because the pH is right around like 9 or 9.5, that means the pKa of this base is at about 9. I can also say the pKb is 5, right? Because remember, pKa plus pKb must equal 14. So that's telling me how strong this base is, right? pKb of 5 is not a super strong base. It's not, it's okay, but it's a pretty weak base. At the full equivalence point, which is point 3, from the pH, which here is around like 5 or 5.5, somewhere around there, estimation is fine. We know that because this pH is lower than 7, it's a weak base. Anytime the pH is lower than 7, the unknown was a weak base, right? From that relationship we talked about on the last slide. And then additionally, we know that whole thing that like the number of hydrogen ions is equal to the number of hydroxide ions. And the way that we solve for that is MV is equal to MV. So if I take the, basically start plugging in my numbers, I gave you the concentration of acid, it's 0.5 molar. I gave you the volume of acid. I mean, I plugged in this number wrong right here. This is supposed to be 0.02. Yeah, what did I do here? Yeah, I flipped this number around. That's my bad. But basically, the concentration of the acid times the volume. Let me correct this underneath it. 2 for 2 on math mistakes today. That's great. That makes me feel great about myself. Okay, so basically, what this should say is the MAVA is equal to, we know the concentration of the acid, it is 0.5 molar. the volume of the titrant at the completion point is 20 milliliters, right? So that is our volume. I'm just going to go ahead and convert that to liters, 0.02. The base, we do not know its concentration. That's what we're trying to figure out. It's unknown. The volume of base was given. It's 20 milliliters, right? So the concentration of the base is unknown. That's just X molarity. The volume is 0.02 liters, right? So then whenever I set these two equal to each other, the molarity is supposed to be equal to the concentration. You just solve for X, basically. That's all you have to do. Just plug and chug at this point. As soon as you figure out what each concentration and volume is, which they will have given to you, that's all you have to do. The volume at this point is what you're using, essentially. So again, sorry that I messed up that math again. I was trying to do something that I must have just forgotten that I was trying to do in the middle of that question. So I'm 0 for 2 on my math mistakes today, but now I know to go back and correct those. So trial run, my bad on that. So basically, that's how I know that the this concentration is supposed to be 0.5, just from plugging and chugging that equation. We're looking for the concentration of the base. We plug and chug. And then finally, we know that the indicator is going to have a pKa of 5.5 because we want it to be changing color right around the pH of the equivalence point right here. It's going to tell us that that reaction is complete. Right. So if you are comfortable with everything that we just did, you are going to be fine for pretty much every single, nearly every single titration question they throw at you. Nearly every single one. Right. Like I said, just keep in mind that whenever, if like maybe instead of HCl, they throw you like H2SO4. That is a diprotic acid. So you'll want to use normality instead of concentration because normality is going to make sure that the number of moles of hydrogen is equal on both sides. But if you can do all of that, you're going to be fine on titrations. The last thing that I really want to add to make sure is clarifying what happens if it's a polyvalent acid or base that we're titrating, if that makes sense. The way that I know how many equivalents something has is based on how many equivalence points the titration curve has. So for example, looking at this curve right here, notice that there's 3 of these equivalence points. So because of that, I know that this is a triprotic acid. It has 3, it starts off as an acid, so of course it's going to be an acid. It has 3 hydrogens that it can donate. So basically, whenever we're just going through each of these protonation states, we are starting off with H3A. And this first little section down here is explained by this first protonation state. So the pKa of this first acid is explained by the half equivalence point. And then we can figure out the concentration using all of that initial acid using the MV is equal to MV stuff. I'm not going to go through all of that right now. Like I said, because this is just kind of like an arbitrary example, and I doubt the MCAT is going to do actual math with polyprotic acids like this. I'll add a clarification just in case, but notice that it's literally just MV is equal to MV. It's the same thing we did before. Plug and chug, figuring out the concentration of the unknown. The second protonation state, this is where we're starting off with what we just produced, this H2A. And this is going to have a pKa that's represented by this second half equivalence point. So because the pH right here is roughly around 5.5, I know the pKa of this second protonation state is 5.5. And then, of course, we can do the exact same thing with all the math right here, right? If we want to figure out the concentration of H2A, we can just plug and chug, right? It took us 10 milliliters to get from here to here. So that's why we used these volumes right here. I'll clarify that here in a second. And then to get to the third protonation state, this is basically picking up with that monoprotic, and we're getting rid of that last proton, deprotonating that last proton. This is going to have a pKa of 9, which I know from this half equivalence point. Then if I wanted to figure out the concentration, plug and chug. Same thing as usual, right? So basically the main thing that they're going to ask you with protonation states is figuring out how many equivalents it has. They might just show you a titration curve and then ask, okay, which of the following acids is this most likely? And so they'll say HCl, HF, H2SO4, or H3PO4. So if they gave you this curve, it would have to be H3PO4 because it's there's 3 equivalents, if that makes sense. That's basically the main way that they'll throw polyprotic titration curves at you. It's very unlikely that they do, but if they do, that's the main thing to focus on. But you can still figure out the pKa of each of these protonation states from all of these half equivalence points. If you really wanted to figure out the concentration and stuff, you could if you wanted to, right? So the last thing that I'll clarify is that, like for example, let's say that you're starting off with H3A and trying to get to the purple point, basically fully neutralizing H3A. If you're using NaOH, NaOH can only produce one hydroxide. This H3A, if we are fully deprotonating it, it's going to require three hydroxide. It's going to produce three hydroxides. So because of that, we're going to need 3 times as much of NaOH as we are that acid, if that makes sense, to make that full neutralization happen. Basically, you're going to be using normality. Normality is going to always avoid. You're never going to mess this up if you always use normality. Basically, you'll just know that the concentration that you end up using is actually 3 molar for NaOH, because you're using, the concentration of this is going to be 3 times higher because it's got a protonation state of 3. But like I said, that's incredibly unlikely to show up. If you wanted to, we could actually dive through the math of what that looks like. But for the most part, just as long as you understand this whole thing with equivalence point and number of equivalents, you're going to be perfectly fine for titration curves and can do all the stuff we did on the last slide. Right? Okay. So literally the last thing that we're going to talk about really quickly. I'm going to go through this super quickly. It's 3 minutes after, like I said, this time that I thought I would end. So I'm pretty close actually to where I thought I would be. But basically, I'm just going to really quickly talk through how the bicarbonate buffer system works. So this is what's in your blood, the bicarbonate buffer system. And it is basically our body's way to carry around and regulate carbon dioxide levels, because carbon dioxide is not very soluble in the blood. Some of it can bind to hemoglobin, but most of it is going to be dissolved into bicarbonate. And you need to know this enzyme carbonic anhydrase, by the way. You need to know that that's the enzyme that's helping this happen in the blood. So basically, the way that this most often shows up on the MCAT is talking about homeostasis, right? So for example, let's just say that someone is hyperventilating, right? They are hyperventilating, which means that their breathing rate has increased. The MCAT might ask you, why are they doing that? Why are they hyperventilating, right? They are hyperventilating in reaction to something. So we are trying to figure out what that would be in reaction to, if that makes sense. So if you are hyperventilating, that means you are increasing your breathing rates, which means that you are increasing at the lungs how much carbon dioxide is removed, right? You are decreasing the blood concentration of carbon dioxide if you are hyperventilating. So because of that, if you are decreasing this reactant, this whole reaction is going to shift to the left. And so that means that this hydrogen ion concentration is going to decrease. And therefore, the pH is going to be increasing, because if you decrease hydrogen ion concentration, pH increases. So this is making the blood more basic. So basically, someone would be hyperventilating in reaction to acidification of the blood. Like, for example, ketoacidosis. This is like what diabetics have, where because they have to rely on beta oxidation more, their body produces more ketone bodies in the blood. Ketone bodies are acidic, so their blood is acidified. So sometimes if diabetics are undergoing ketoacidosis, a symptom, a reaction of that is hyperventilation. If you hypoventilate, it's literally just the opposite across the board, right? That's going to be something that's happening in reaction to having too basic a blood, which is not as common as having too acidic blood. But basically, decreased breathing, decreased CO2 removal leads to increased carbon dioxide retention of the blood, meaning that you have more of this reactant. The reaction is going to shift to the right, increasing how much of this hydrogen ion there is in the blood, which decreases the blood pH, acidifies it. But that's in reaction to the blood becoming more basic, if that makes sense. Just got to make sure that you understand, are they just simply asking what happens when you hypoventilate, or are they asking why are they hypoventilating? It's an important thing to make sure you understand. The other thing that we can do to regulate blood pH is what goes on in the kidneys. That basically the kidneys will control what's going on over here. The lungs control carbon dioxide levels, and that's how they can control pH. The kidneys can directly control bicarbonate and hydrogen concentration. So basically, if they remove if they secrete hydrogen, that means they are putting it into the pee, into the urine, into the filtrate. So that is decreasing how much hydrogen or bicarbonate there is. That means this whole reaction is going to shift to the right if you're decreasing a product, which is going to compensate by increasing the pH of the blood, if that makes sense. Basically, getting rid of hydrogen ions in the kidneys is going to make the blood more basic. Just by decreasing how many hydrogen ions there are here. Yeah, that makes sense. This happens in reaction to ketoacidosis. The blood is too acidic, so we start getting rid of these hydrogen ions. We're getting rid of them essentially. So if you're absorbing in the kidneys, that's the opposite. That means you're putting stuff from the filtrate back into the blood. This is something that the proximal convoluted tubule mainly is doing. If you know your renal systems, that is one of the lectures that's planned at some point in the future. But basically, what happens here is because you're moving hydrogen ions into the blood, you are increasing the hydrogen concentration of the blood, therefore decreasing the pH. You are acidifying the blood. This is something that would be happening in reaction to basic blood. So that's just the last thing that I was going to say is that like the renal system is really slow. This takes like weeks to months. This is really fast. So that's why like if someone has an anxiety attack or ketoacidosis, this is the main thing that we're going to notice. This is much more so long-term pH control. But yeah, okay, so that's it. That is literally everything that you might need to know about Gen Chem acids and bases for the MCAT, right? Like I mentioned, the on-key deck and recording will be sent out sometime tomorrow. I don't know how long it's going to take the recording to compile and compress and stuff like that, but I will send out that email whenever it's done. Highly recommend checking out my website for future lectures. Like I said, I have one lecture that's going to rotate once a month. So if you wanted to be patient and wait, you could get every single lecture for free over time. It's just going to take quite a while. And then all of the other paid lectures, they're going to be, it's the same exact topics. They're just offered more often if you wanted them at a more accelerated rate. That's just a way for you to kind of support me in everything I'm doing. So I really appreciate that. I also really appreciate you guys being here. First lecture of its kind. I've got a lot of people to send this recording to, but yeah, I really appreciate that. Yeah, thanks for the kind words. Hopefully this was helpful. I'm glad I could offer this for free. Like I said, I can't do this all the time because it's a lot of time and effort, but glad I could offer it. I'll of course appreciate any feedback. I'll throw my email up on this last slide, but yeah, I will send everything to you guys later. Like I said, I am going to go back and do those math problems after this, just so on the recording they're there, but yeah, for you guys being here. Okay. There's got to be a way for me to get back to this slide faster. Okay, there we go. Example problems. Where was that? Right here. Okay, so if you're still watching this on the recording, okay, I see. Thanks, Ray. I appreciate you. Basically, I recommend having your that flow chart up because that should help with a lot of this stuff. But basically, just to kind of go through this pretty quickly. So, like I said, so notice here that we were calculating pH, but I gave you basic stuff. So I'm just keeping in my mind that I know that whenever I calculate pOH, I'm going to have to swap it back to pH, which is pretty easy to do. It's just the pH plus pOH is equal to 14. Really easy to do. Don't have to worry about that. Just make sure you don't forget about that. Okay. So writing out this reaction, sorry, not KH. What we have is we have NH4OH, which is a weak base. So we're going to have a bidirectional arrow is dissociating into ammonium ion. Yeah, we're going to be using ice. Perfect. Ammonium ion, is the NH4. And then all of these are aqueous as well as hydroxide ion, right? So kind of like I mentioned earlier, I recommend looking at the answer choices first. So I've added a base to water. So what does that mean about the pH of the water? Is it going to become more basic, like above 7, or is it going to be below 7? You don't have to answer. Yeah, it's going to be above 7, right? So it makes no sense for A and B to be possible, right? I'm already down to a 50-50 shot at this point. And like these numbers are pretty close to each other, the 10.6 and 10. So we'll still go through and do the math. But basically, that's what I'm saying to like help you eliminate answer choices. Just immediately once you identify acid or base, go through your answer choices. So from here, like you said, we're going to be doing an ice table because this is a weak acid that I only gave you the concentration, sorry, weak base that I only gave you the concentration of the base in the KB. Pretty much anytime they give you the KB value, it's a pretty good indication you're going to be using ice tables. Not always, but pretty good indication. So if I have 5 times 10 to the negative fourth, if that's my concentration of NH4OH, basically, I know that all of this hydroxide, that there's only one equivalent, if that makes sense. Like there's no, it's not like there's two equivalents or anything. All of that hydroxide, all of this NH4. Oh wait, sorry, I'm getting way ahead of myself. Sorry, I'm talking about strong acids and bases. My bad. Okay, ice table. Sorry, this is what I'm starting off with. It will change by negative x, and at equilibrium, where basically, like I said, you can ignore the negative x whenever we're talking through ice tables. So just my equilibrium concentration is going to be pretty close to what it started off with. For NH4 and OH, they started off at 0, but just so you know, sometimes they will specify a starting pH. Sometimes they will say the pH is 8, which means that you are starting off with a hydroxide concentration. So you just would add that right here, just as an added layer. That's rare, but I'm just letting you know that that's what you would do. So these things, we're going to increase how much of them there are. We're going to add plus X. So just down here, their equilibrium concentration is just going to be X, right? Monoprotic everything. Don't have to worry about equivalence, doubling, anything like that. It's actually not very common that you'll have to do this math with a polyprotic acid or base, because that's going to make the math really complicated. You're going to have to do cube roots. Cube roots of stuff, which is no fun at all. And the MCAT is not going to make you really do cube roots. So from here, I know that my KB, which is equal to 2 times 10 to the negative fifth, which is equal to the products, which is x times x over the reactants, which is 5 times 10 to the negative fourth. I can simplify this to saying that x squared is equal to 5 times 10 to the negative fourth times 2 times 10 to the negative fifth. Gonna multiply the 5 times 2, that's gonna give me 10. And then anytime I'm multiplying 10 to the negative fourth by 10 to the negative fifth, I'm gonna add these exponents. So 10 to the negative fourth, negative 4 plus negative 5 is gonna give me 10 to the negative ninth. I'm going to simplify this really quickly because their scientific notation needs to be between 1 and 10, not including 10. So I'm going to move this decimal to the left, which means that I'm going to make this exponent a little bit bigger by 1 decimal point, which is 1 times 10 to the negative eighth, basically in the positive direction, if that helps. Again, that's something that I go through in my first math video that's already on YouTube. So, and this is equal to x squared. We're going to take the square root of this, and basically what we get, sorry, this is scatterbrained all over the place, is that x is equal to 1 times 10 to the negative eighth, which is divided by 2, since we're taking the square root of it, which is 10 to the negative fourth, right? This is my hydroxide concentration. And since this is my hydroxide concentration, 1 times 10 to the negative fourth, just so you can follow my arrows, since this is really scatterbrained at this point. 1 times 10 to the negative fourth is equal to 10 to the power of negative POH. So your exponents are going to be equal to each other. POH is equal to 10. And therefore, pH equals 4. Right? So this is quite honestly kind of the worst case scenario that they're going to do. Like realistically, the hard thing is knowing how you're supposed to get from point A to point B. What they also could do is, instead of giving you the exact concentration, giving you mass and making you figure out the molar mass, pulling the volume out of somewhere to calculate the concentration and then going from there. That's the other added layer. But this is kind of like the worst case scenario of what they're going to do. If you can do these ice tables pretty comfortably, which they're pretty simple, you're going to be fine for most weak acid questions. Again, this takes a little bit longer. So this is definitely one of those questions that I'd say, types of questions that I'd say to make sure that you're practicing. But yeah, from there, moving on to question 2. So they have a buffer solution. So we're going to be using the Henderson-Hasselbalch, right? Buffer solutions, you're pretty much always going to be using Henderson-Hasselbalch. I gave you the number of moles of acetic acid and the number of moles of sodium acetate in the water. So we could go ahead and calculate the concentration because technically the the Henderson-Hasselbalch equation uses concentration, not moles. But I'll show you why that doesn't actually matter here in a second. So we have acetic acid and its conjugate base, right? We then add 25 milliliters of this strong acid, 1 molar concentration of HCl. Then it asks for what is the pOH. So that's something that like I would highlight in the question just to make sure that I knew, okay, they gave me a whole bunch of acid stuff, but they want a pOH. So if they gave me a weak acid, acetic acid, and a strong acid, what is the pH going to be? Is the pH going to be acidic or basic at this point? Just arbitrarily, if we're adding acids, it's only possible for the pH basically, to be acidic, right? So an acidic pOH is greater than 7 because it's like the inverse logic. An acidic pH is less than 7. An acidic pOH is greater than 7. So you can immediately eliminate A and B, right? That is, wait, yeah, okay. I don't know why my brain fart. So we are already off to a good start. We're already, even if we just guessed at this point, we're already at a 50-50 chance instead of a 25% chance. So from here, I'll go ahead and write out the Henderson-Hasselbalch equation. pH is equal to the pKa plus the log of the conjugate base concentration divided by the acid concentration. And then remember, basically where we're going to start is by plugging in the pKa, which they gave. 4.76. And all we have to do is just ask ourselves, is there more conjugate acid? Is there more acid or conjugate base? So even though we technically should be putting this into a concentration, they both are, they're in the same solution. So they're going to have the same volume. And therefore, like the number of moles is going to be equivalent to the concentration, if that makes sense. We don't have to convert one to the other. We can get the same conclusion, if that makes sense. So there's slightly more of the acid than the conjugate base. So if there's a little bit more acid, what is that going to do to the pH of the solution? Is it going to make it a little bit more basic or a little bit more acidic than the pKa? Yeah, more acidic, right? So I'm just looking for basically plus something, but I just know it needs to decrease. And that's what my pH is equal to. Right. So likewise, again, we're talking about pOH here. So if I kind of flip this around, I know that my pOH, let me do a little bit of rearranging here. Actually, no, I'll just go ahead and estimate it just to make things simple. I'll just decrease it to like 4.5. Let's just pretend that like the pH is equal to 4.5, right? Basically from here, I know that the pOH is going to equal roughly 9.5. And notice that C is really close. We can eyeball it. That's our answer. The other thing that I was going to say was in order to get a pOH of 8.9, we would have to get more basic from this number right here. So that would be an answer where if there was more conjugate base than acid, the answer would be 8.9. So you don't even necessarily have to do any actual math to make that final estimation. You just have to know what direction we're going, if that makes sense. That's just the last thing that I was going to add. You technically didn't even need to estimate an actual number here. You could just know that, okay, 4.76, that's roughly a pOH of 9.25. So it needs to be a little bit higher than 9.25 since it's the pOH, which is the inverse of everything. Again, that's a little bit complicated, but basically, like I said, Henderson-Hasselbalch is pretty easy. So yeah, okay. Those were the two example problems. That's like I said, hopefully just looking through that flow chart makes that a lot easier. But